will see a lot of patients, and thus uh, it will be it will be contributing more data for the local model training. So while also we have included a public, primary healthcare center located in some other remote area or in some rural area, so where the number of patients visiting primary healthcare center may be very, very less. So that the number of data being contributed by that local center is going to be very, very less compared to rest of the clients participated in this federated. Okay, so this is in terms of both sample size as well as in terms of class distribution. Because in case of hospitals located in district headquarters, so we would see a diverse set of patients, people with different health conditions would be visiting the hospital, so that they contribute a lot of data for research, right? Though they get treatments, of course, they are also undergoing a lot of diagnosis, consultation with doctors, and then their previous history. So all of them would likely be recorded at the hospital. Yeah, but when someone goes to primary healthcare center, and they are likely contribute less data, because there would be not much of diagnostic centers, diagnostic, the biomedical diagnostic machines won't be available in primary healthcare centers, and they mostly likely, mostly they record only the oral conversation that they engage with patients, right? So that is something that would probably be stored somewhere. So the class distribution is going to be fairly less compared to other big hospitals which are in the loop of the federated learning. Okay, so that is where in practical scenario we are we would be mostly working with non-IID data, and it is very difficult to see IID kind of data. And here is the sample which I have given, but it is not something that we can observe in any practical setting. Right. So accordingly, this as no Fed average is very sensitive to non-IID data, because when you run Fed average in a non-IID setting, then you can't really see desirable training happening in this setting. Okay, so Fed average would not be the right choice when your data distribution, underlying data distribution in terms of both sample size and then class distribution are completely ununiform, non-uniform. So there are various, we will revisit the various other algorithms which are like an extension to the Fed average mechanism. So before that, there are few other important basic steps to highlight upon. Let us quickly go through them, and then we'll get into the aggregation schemes as such. So there are different types of federated learning. So first one is called horizontal federated learning, and then vertical federated learning. Then there is something called federated transfer learning. As we all know, transfer learning is something that you know helps model to retain some of the knowledge that it has already gained from some other domain. Okay? Let's say we widely see around, people use YOLO models predominantly these days for any object detection task, and people tend to have this YOLO as their one of the important choices, or it would act as a very strong and standard baseline for comparison, especially when it comes to object detection. Right. For example, YOLO model has been trained on, let's say, lot of kinds of objects. So now, let's say we wanted to build an object detection, let's say for underwater object detection. Let's say we want to build a novel model for underwater object detection. So now, what we can basically do, we need not really train model from scratch. So let us just take some standard object detection model like YOLO, and then we can bring it to our domain, and then try to just alter only few of the parameters of the existing YOLO model. And as you just we just inject the knowledge that model is supposed to learn from our data set is what only fused into the model, and let the remaining knowledge of the model be retained as it is, so that we can still use. I'm not sure whether YOLO models are trained on underwater object detection, but in case if it is not trained with underwater objects seen in underwater scenario. And now we are actually adding some extra knowledge from our domain to the existing model, so that existing model can perform well in underwater object detection. Okay? Because it knows what are objects, and it knows how to identify or detect objects from the given image. Okay? So this general knowledge would certainly help in any specific domain where it can certainly perform well. Okay? So the same way we can even use federated learning, so which means we use some existing models with existing weights. So without training model afresh, no, no, training all the weights involved in the model, we just freeze certain weights of the model as it is, and then we probably try to fine tune only probably the last few fully connected layers. So as we all know, right, when you consider CNN kind of network, convolutional neural network kind of networks, neural network architecture, so where we used to basically retain the feature representation layers as it is, because probably the way how standard model learns features from images, it should be probably the right way to learn even features from other domains as well. But the only tuning that we wanted to do is at the fully connected layers of the network. Okay, the last few layers where the classification decision is basically taken by the model. Okay? So only those weights are going to be altered by the model. Okay, we can even do the implement federated learning even with the notion of transfer learning, so which where the global model will try to update only those parameters involved in the fully connected network, and not the feature representation layers. Okay, those weights are going to be intact for all the clients as well as the global model. Okay, that is something called as federated transfer learning, and widely we tend to use either of these, horizontal or vertical federated learning. Okay? So horizontal federated learning or sample based. Okay. For example, if you have in a simulated setting. Okay. So in a simulated setting, let's say we have now 10,000 samples. Okay. What you can do, 10,000 samples in the sense you have 10,000 rows in your data. Let us assume that you have your X part, which means your X part, X1, X2, and so on and so forth up to Xn, and then you have your Y part. And this is your data. And let's say you have these 10,000 samples. Let's say you have row 1, row 2, row 3, and so on and so forth up to 10K. So now you just wanted to simulate, and you wanted to now distribute this data across, let's say, some number of designated clients, and then you wanted to learn in a federated setting. So in that case, so one option is that we have is, in case we divide, let's say we have 5 standard clients in our model, so that you can divide this 10,000 instances by 5, that you get
ఈ
2K
మళ్ళీ క్లోజ్
instances
ఫ్రెండ్
each.
అని చెప్పావు కదా మళ్ళీ ఏంటి అని
So we have two thousand instances for each client. So I hope I'm audible to everyone.
Yes, sir. We are
Oh,
listening, sir.
thank
Yes,
you.
sir. Yes,
Thank
sir.
you. Thank you. Thank you. So we can then distribute these 2K samples to all the participating clients, and then we can learn from. Okay. In case if our data distribution, if this is the way we distribute data based on samples, then it is called horizontal federated learning. On the other hand, you can also use a vertical federated learning, where you are going to distribute, you are going to split data based on features. Okay, we have n features, let's say x1, x2, x3, say x4, and so on and so forth up to xn. So instead of dividing data by rows or the samples, so we can divide data by columns. Okay, for example, just let us send these features along with y label. Okay, y label is also important because we are discussing about predicted learning being used in supervised setting. So now to one client, you can send only data containing features from x1 to x3 along with y label, and then to client 2, probably you can you can share, probably to client C2, you just distribute data, let's say containing features from X4 to X10. Okay, something like this. In case if you split data this way and then you distribute it across different clients for learning, then such federated learning is called vertical federated learning. They are also called as feature-based federated learning. Okay, so it basically talks about based on type of data splitting you are going to have. I'm not considering actual real world application because in real world application, data itself gets generated at local sites, but I'm talking about the simulation setting. So when it comes to simulation, where you have a huge data, but assume that you wanted to do it in a distributed manner. Okay? You just wanted to test the efficiency of, let's say, federated learning, especially to compare this horizontal and then vertical federated learning. So what we can basically do is, for one setting, you can split data based on samples, and in one setting, you can split data based on features. Okay? So that different clients are going to actually operate on different features in the case of vertical federated learning. In case of vertical federated learning, each sample on which the vertical federated learning is operating is completely on different set of features, because C1 is working with only three features and C2 is working with, let's say, X4 to X10, and those features are not seen in data distributed to client C1. Okay? So every client is going to completely operating on a new set of data of probably same instance. Okay, of the same sample, data from same sample are actually distributed to different clients in case of vertical federated learning. In case of horizontal federated learning, um, the field wise, no, which means the row wise data are preserved. Okay, so for example, in case of healthcare setting, client one will have, let's say, details from patient P1 to P1000. So while client 2 may have data samples from P no, 10,000, sorry, 1001, 1001.
Sir, your
Sorry,
screen is not visible. Yes.
yes, yes, I'm
Yes.
sharing my screen
Yeah,
actually.
yes.
Thank you.
Thanks.
Okay, I lost all my scribblings here. Okay, but anyhow, right, in case of in case of vertical learning, so we are going to divide data based on features, and in case of horizontal federated learning, we are going to divide data based on samples. So, for example, samples starting from S1 to, let's say, S1K, will be sent to client C1, and client C2 will get samples from, let's say, S1K plus 1 all the way up to S2K. So something like this. Okay, so all the data samples in case of horizontal federated learning is going to have same set of features representing different element of data instances. But while in case of vertical learning, again, as the case may be, we can choose to go with either horizontal federated learning or vertical federated learning. There is a use case here. For example, especially when you try to learn from data available at multiple hospitals. Multiple hospitals having no samples of, let's say, same uh, patient record format. Yeah, assuming that there is a format for representing or storing patient information. So if all the hospitals participating in the federated learning are maintaining patient records with, let's say, same format, yeah, like patient ID, patient name, and then patient other demographic details, and then again various vital indicators, and then other specific diagnostic signals. No, okay. Assuming that all the hospitals are following same schema for the data. Yeah? But the instances are going to be of different patients. Of course, we are dealing with different samples at every client. Okay? So S1 represents details of patient one, and then S2 represents patients of no, details of patient two, and so on and so forth. But on the other hand, when it comes to vertical federated learning, so we can consider a banking scenario where a bank and an e-commerce platform are sharing user details with each other. So what can really happen here? See, here in case of this use case, both client C1 as well as C2 are going to operate with same client detail. Let's say the instance is going to be same. Let's say S1, because the part of S1 which is available at client C1 is obtained from bank. Let's say it's a bank. I mean C1 as bank, where there is a client S1 and who is maintaining some, let's say, some transaction history and then some current balance and then his or her other no details like name, age, profession, family size, and then annual income, and then how much amount of tax that the client is paying, and all such details. Okay, but on the other hand, C2 is your e-commerce platform. E-commerce platform where the same client S1 is also participating because we all do have bank accounts and we also participate in no e-commerce transactions, like we purchase items from Amazon, Flipkart kind of e-commerce systems, right? So now assume that bank and then e-commerce platform now wanted to have some learning happening on data that they individually maintain at their local servers. Okay? So now S1 here at the e-commerce site will have certain features, okay, which are not same as that of features seen in the banking scenario, right? But the users are same here, but the data that they have on different clients are completely different. Okay, so in e-commerce sites, probably our monthly transaction history in terms of items that we frequently purchase, so all such details would be there. Okay, so now maybe for targeting some particular user, targeting some particular. ये कहाँ है? मुझे पता नहीं, मुझे पता नहीं. Sorry. Right.
Yes, sir.
Yeah. Right. So now this setting could be preferred in order to target a particular customer, let's say with some offers also due to the problem in, let's say, aggregating data into a single server. Yes, of course, we decided to go with vertical federated learning so that features being used at different clients are completely different. So here is a detailed comparison between horizontal and vertical federated learning, which I am going to skip now. Yes, as you can visually see here, right? So here the client one is going to have a split, let's say, sample wise from row wise. Yeah. And on the other hand, in case of vertical federated learning, the client one is going to have, let's say, few features like F1, F2 along with Y label. And then party two, party B or client two is going to have features, let's say, F3, F4 along with Y label. Okay, this is how it is going to be split. And the same use case that we have just seen in the previous slide is what shown here. So again, it depends on what kind of application we are dealing with, especially if you want to learn, let's say, from um, a different entity, okay, entities which are of different types. Like a bank is one entity, and while insurance is one entity, and then e-commerce is one entity, but all of them are common when it comes to a domain, which means all of them are somewhere or the other way dealing with some form of finance. Okay, though banking is different from insurance and then e-commerce is different from banking, right? But what is common in all this is some kind of online transaction is actually taking place there, and all of us are equally participating as well. Okay, all of us own accounts. Let's say all of us own some insurance, or you can even think of including loan stuff also into this thing. Maybe one client where all loan information of a particular client is particular user is actually kept. So all of us probably have ongoing loan. All of us have some live insurance with us, and then all of us have some running bank account, and all of us even do equally participate in e-commerce transactions. Okay, but all data are completely different from each other, but all of them are maintaining probably the same set of user details. But on the other hand, in horizontal federated learning, where the entities are same, homogeneous entity are being participating. When you have a real life setting where you have to deal with, let's say, hospitals, which means hospital A is no different from hospital B. Though they have different set of doctors, different set of medical practices, but the kind of data that they gather from patients are going to be same. Okay. So accordingly, you can understand what kind of federated learning are you working with, whether it is vertical or horizontal. Okay. So now we are getting into our actual topic, that is aggregation. So when it comes to aggregation, yeah, only aggregation that we have seen so far is Fed average, and for which we have seen the primary, the standard skeleton of the algorithm that I have shown in the previous session. So here, there are certain characteristics of aggregation, or the way we do aggregation. So besides the core logic of aggregation, so how are we going to exercise different aggregation algorithms? So accordingly, it can be used in various ways. The first way in which we can use aggregation is synchronous aggregation. Probably I can first look at this logical flow of synchronous aggregation, and then we'll get back to this theory. Mostly, the theory would be self-explanatory. So once we understand this workflow. So as we look here, there is a central server where the global model is kept, and then we have this local site 1, and then local site 2, and then local site 3. Okay. Here I'm considering a kind of edge devices here, where the local site 1 is actually the mobile phone, and then local site 2 is drone, and then local site 3 is CCTV camera. Right? So each one of them are actually contributing some data, let's say, about the environment. Okay, so let's say you are using this system in order to learn about some sort of surveillance data. Yeah, CCTV is kept in a central junction. Let's say consider a traffic scenario where a CCTV is kept, and then also for the local surveillance, the local administration has even deployed some drone. So that drone is again monitoring the city or the vehicle movement, vehicle movement at the at the aerial surface. And then again, mobile data is being used, probably uh, multiple mobiles. I'm just considering only three of them here. Now, as devices are different here, right? So one is mobile phone, one is drone, one is CCTV, and all these devices operate at different configuration, right? So mobile phone is probably considered more powerful than drone, and probably drone is considered more powerful than CCTV camera, or even CCTV camera could be considered more powerful than drone. Okay, but there is some heterogeneity seen here. Now, as the mobile phone is considered, device with better configuration compared to rest of the clients. So the mobile phone actually gives or update server at first. Okay. So now what happens? It is a synchronous aggregation scheme. So client one, after sending its update to the global server, and client one supposed to wait till server is responded with rest of the clients participating in this federated learning, right? So now after some time, after this amount of this much amount of time, and local site 2 now updates server with the local update, and then again server local site 2 supposed to wait till this time until local site 3 actually updates server with the local update. Okay, so once server receives local update from site 1, site 2, and then site 3, then server runs this aggregation algorithm at the server side, and then it is going to aggregate the parameters that it has received from all the three clients, and then it is going to share the aggregated updated model with all the clients at the same time. Okay. Now again, yes, some local model training is happening at local site 1, then it updates the server with the updated model. As the configuration of this device is better than the rest of the participating clients, it is likely, understood that this model will quickly update the server with a local model training. Okay, as the configuration is very limited, constrained here in local site 2 and 3, so it is actually taking more time compared to other high config other devices with high configuration. Right. So again, once server receives updates from all the local models, then it will run this aggregation algorithm, and then it will update the local. It will then share the aggregated model with all the participating clients. Okay? So this is what synchronous aggregation is all about. On the other hand, we have asynchronous aggregation, which means why should the server wait or why should the client wait for rest of the clients to contribute their parameter update to the local model for aggregation? So why don't we do aggregation in an asynchronous manner? For example, now already there is a global model, and then there is a copy of global model available locally, and now locally you run one round of training with whatever data we have at local site, and then soon after server receives model update from local client, and it will immediately aggregate it with, because aggregate in the sense global model already has some initial set of parameters, and then the model updates comes from local site 1, and whatever that this global model receives from client 1, it will immediately aggregate it with what it already has. It doesn't wait for all the clients to equally participate, or it doesn't wait for all the clients to receive model updates so that it can go for aggregation. So aggregation doesn't wait for other clients which are part. Whatever update that it receives from the first client, it will immediately update that local client with an aggregated model. And then similarly, when it receives update from model 2 or the local site 2, it immediately again run aggregation algorithm, and then it updates a client with an updated. Again, when it receives, see, by the time, as we can observe here in this timeline diagram, by the time it receives, by the time server receives first update from third client, and it has received, let's say, second update from first client. Okay, so now what happens here is aggregator is actually doing a lot of work, because as we can see here, so only probably 5 different updates that the is server has seen, and for every time it receives update from local client, it is going to run this aggregation algorithm. So while in the case of synchronous aggregation, so only if though it has received, let's say, 6 different updates, right? So twice from each of the participating clients, but the number of times aggregation algorithm has executed here is only twice, because it doesn't immediately run aggregation algorithm soon after it receives an update from a local client, because server knows what are the local clients which are participating in this learning process. So it will wait until it gets update from all the local participating clients, and then it will run aggregation algorithm once in order to consolidate weight updates that it has received from all the clients. Okay? So that the aggregation algorithm is going to be taking probably less time, right? Because aggregation algorithm in case of synchronous setting is actually taking less effort, while in a synchronous setting, and the global model has to run aggregators so frequently that whenever it receives an update from a local client, it's supposed to run the aggregation. That's the difference between asynchronous and synchronous aggregation. Again, what is best, whether it is whether synchronous is best or asynchronous is best. So, answer to this question generally comes from the experimentation. We need to conduct a rigorous experimentation in order to realize that. But one other simple observation we can make. So, especially when when the when clients are completely heterogeneous, as per the setting we have considered here. One is mobile phone, drone, and then CCTV. All of them are operating at different speed. All of them are operating at different configuration. Underlying hardware are completely different, the compute capability are different, RAM memory is different. So since all these devices are all these devices are No, it's a basically a cross-device setting, right? As we have seen comparison earlier, right? The devices involved in the federated learning could be cross-device or cross-silo. So cross-silo in the sense you see homogeneous configuration. So all the participating clients will have same hardware, no, more or less same hardware configuration. Because all of them will have, let's say, same amount of memory, same amount of compute, and same amount of other no security features like a RAID or so. For example, all of them are reliable, equally reliable. All the devices participating in the federated setting are equally reliable. But here, probably mobile is considered more reliable, while drone and CCTV are considered less reliable because these nodes can very quickly fail. Because a drone can probably lost its battery and then it may go down suddenly. So what if such thing happens during the training? The drone is running and then it is also participating in the learning process. But suddenly, due to energy loss, then drone may immediately get down. So when it gets down, and what if server waiting for response to come from drone? Yeah, drone has already failed and already it is out of the service, which means out of participation. And now if server is keep on waiting for a response to come from drone, then the other clients are now in idle state. And that is something that is not desirable. So if in such a setting, it is better to go with asynchronous aggregation. So in order to deal with this type of device failure, no, it's not needed that server supposed to wait, till it gets all the updates from all the participating clients. Okay, so it is a good trade-off that we can run probably more rounds of aggregation and instead of no just waiting for updates from other participating clients, which are very less reliable. But in the case of cross silo setting, it is good to basically go with synchronous aggregation. So where all the nodes in the federated setting are equally reliable, all of them are having equal compute and then other memory and then other no underlying hardware configuration. So all the devices are equally powerful so that it is okay that server waits till it gets updates from all the participating local clients. Okay? So especially when heterogeneity is seen in terms of devices participating in the setting, it is better to go with asynchronous aggregation. If all the devices participating in the setting are homogeneous, then it is better to go with synchronous aggregation. Again, the choice of aggregation could be different. Okay, this is the kind we apply. This is the way we apply aggregation. So again, we do have choices of aggregation algorithms, and then we have tiered aggregation. So tiered aggregation in the sense, so we are going to have multi tiers, right? As you can see here. So in this setting, there are different works which are highlighted here, and you can go through the research paper to get more details about this. I'll just give you a brief idea about what tiered aggregation is all about. So instead of keeping treating all the devices individually, all the local devices individually, it is better that we group them or tier them based on some sort of no homogeneity seen across different participating clients. So as there are multiple mobile devices participating in this setting, so we can group all of them into, let's say, called tier one, and then all the drones. Though the drones are different, maybe there could be slight heterogeneity seen across all the drone kinds, but still, as they are all drone, we just group them into tier two, and then we group all the CCTV cameras into tier three. So now we have clubbed participating clients into different tiers. And now what global model can do, as soon as it receives the updates from all the devices which are from tier one, what it can do, it can consider applying aggregation based on that. So which means again the tiered aggregation can happen in terms of either asynchronous or synchronous. Okay? Tiered aggregation can be a can be again seen as asynchronous tiered aggregation or synchronous tiered aggregation. So the diagram here actually shows the synchronous tiered aggregation where it receives first updates from all the devices from, let's say, tier one, and then it receives updates from all the devices of tier two, and then it receives updates from all the devices from tier three, and then finally it goes for aggregation. Otherwise, soon after it receives update from tier one, then it can immediately go for aggregation. Yeah. So this is something called tiered aggregation because the tiered aggregation actually helps us in many ways, especially they are grouped based on underlying hardware configuration that it carries. Okay, at least we wanted to actually, not to completely deal with, high level of heterogeneity, and just to handle heterogeneity in a graceful manner, we are just grouping them into different tiers so that at least within every tier, you see that devices are homogeneous in nature. Okay, but across tiers, it is going to be heterogeneous, but at least within tier, it is going to be homogeneous. And then we have this hierarchical aggregation where we can introduce one more extra layer, extra level in the federated learning. Let's say we do have all the local clients running here, and then local models are not directly reporting to the central server. So it has, let's say, one other level of edge nodes, which means these are all the edge nodes. They're edge nodes, and these could probably be like workstation grade systems. These may be like workstation grade systems. These edge devices are actually sharing its update with the workstation, and then workstation will also run some aggregation. Okay, which means it is this local system, this workstation receives updates from uh, all the edge nodes which are of mobile node type, mobile device type, so that this local workstation will deal with only devices which are of this kind. Yeah. Similarly, this workstation is dealing with the devices of this kind. This local workstation is dealing with devices of this kind. So that we are, if you could observe here, we are gracefully handling, the notion of heterogeneity. Right? So that now, since all these workstations are going to be homogeneous in nature, so that it would be easy for the server to move with homogeneous clients. Yeah, but the rest of the again at the workstation level, and this workstation is actually dealing with all homogeneous devices. But across, if you look at the entire architecture, we do have heterogeneity, but heterogeneity, dealing with heterogeneity is quite challenging, right? The node failure will severely cause the overall learning process. So in order to avoid it, and we go with this kind of hierarchical way of arranging various participating local clients so that we are able to take a better outcome from this overall learning. Okay, so this is called hierarchical aggregation. This is again another popular aggregation algorithm. And again, one more challenge we have in the case of federated learning is client selection. How are we going to select clients? Yeah. So especially in case of cross device setting, client selection is very, very important. In cross silo setting, client selection is not necessarily we need to devise a client selection strategy because all the participating nodes are homogeneous and all of them are equally equipped. So the chances of facing node failure is going to be very, very less. So no need to even think about client selection, and we can equally allow all the clients to participate in the learning process. While in case of cross device setting, where we see thousand or even millions of devices participating in this federated learning, where devices configuration, let's say, varies from high configuration to extremely low configuration, like edge devices to all the way up to workstation grade nodes. Right. So when we have such a setting, then it is better to choose clients accordingly. You can choose clients based on how much amount of data that each client is contributing. Okay, probably you can select for current round update. There are, let's say, 100 clients participating. So assume that there are 100 clients participating, and what global server can do, it can just limit the number of updates that it's supposed to receive from clients. Let's say when it receives updates only from 10 clients, 10 reliable clients among these 100 clients, soon after it receives it, then the server can go for aggregation. Or server need not really wait for all the clients to respond, and it just selects client based on certain qualities, like maybe choose 10 clients out of 100 clients based on amount of available data with them. The data, the clients which are holding no reasonable amount of data could be chosen for model aggregation or the weight aggregation, or clients could be chosen based on its underlying configuration. Okay, there are several factors we can consider while choosing client for updating weights at every rounds in the federated learning. Yeah, so you can choose clients based on data heterogeneity kind of data, and you can choose clients based on device heterogeneity. You can choose clients based on device unreliability, which means you always choose to receive updates from reliable clients. So if clients have, you can introduce some notion of probably trust or reliability factor. And if the reliability factor is less, then let the server do not consider or do not expect weight update from such clients. Maybe over time, when the reliability factor increases, so then such client can participate in the learning process. So these are some of the state-of-the-art client selection approaches we see from the literature. You can go through them offline. Yeah. So let's get into this. No, the actual aggregation mechanism. So here is the outline of Fed average mechanism. So it is formally defined this way. No, right. So there are this f of w is the function which is running locally, right? It is the cost function of the optimizer, which means this is something that we wanted to optimize locally. Okay, you can think of this f of w as the loss function that we wanted to minimize. Loss is something that we wanted to minimize. It is a local loss. There are k clients participating in the federated learning, and then the loss seen at every local client is what represented as f of w, while the f of w is the global loss, the of measured by the global model. Okay, and then we are just going to simply aggregate it, keeping all the clients with equal priority. On the other hand, you can also assign some sort of priority to each of these updates. Okay, you can multiply this. You can assign some sort of weighting factor to these laws. Okay, that depends on how reliable the client is, how powerful the client is, and how much amount of data that the client has. So based on that, we can probably come up with a weighting factor. It's a standard, no, federated setting. Now, it has been experimentally observed that when such algorithm, Fed average algorithm, is used in IID setting, and it is seen that it actually improves the accuracy of the model. Yeah, I'm just showing here accuracy only here. You can any other standard evaluation metrics you consider, and Fed average mechanism is found to be very, very effective in case of IID setting. While data are not fully IID, it is somewhere in between. So which means you have kind of mild non-IID, which means the clients are different only in terms of number of samples, but the class distribution are same. Okay, you can probably consider uh, 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 such a kind of non-IID as mild non-IID. Okay, which means it differs only in terms of number of samples, but the class distribution is even. Class distribution is even. But on the other hand, both the number of samples as well as the class distribution are extremely different. Okay, in such a setting, we observe that the Fed average is actually underperforming no, very badly, right? It is not performing good, as we can see here. So this is the big challenge that we face while using Fed average in non-IID setting, as Fed average generally prefer to work in IID setting, but not on mild or severe non-IID setting. Okay, as the non-IID, the level of non-IID actually increases, as we see that there is a decline in the model performance in terms of accuracy. Right. So there are a lot of statistical heterogeneity that you can observe from data. One is, yeah, it could be different in terms of sample size, number of samples you have at every local site, or it could even differ in terms of class distribution. So besides that, you can also see certain other things. For example, yeah, again, coming back to this MNIST use case. So we see in this case that client one sees only digits from 0 to 2, and client 2 sees only digits from 7 to 9, and so on, because the class distribution is uneven across clients. And then when it comes to the other kind, for example, let us consider hospitals are the participating entities where all the hospital uses MRI scanner, but they use different protocol for capturing MRI, because MRI are of different kinds again. So maybe if you use protocol 1, then that MRI results would be different. But though it is MRI, doctors will be able to interpret it. But when it comes to automated training or learning from such a representation, probably learning from MRI images that uses protocol 1 may be certainly different from learning from no MRI capture using protocol 2. Okay, so different hospitals uses, let's say, different protocols or different mechanism, to collect MRI scan reports. Okay? So in such cases, what happens, probably the number of samples may be same, but actually the kind of data that we have, kind of data at high level is same, but kind of data that we see, if you inspect it from the feature level, it could be different. Okay, so these are different, heterogeneity that we observe again when it comes to yes, clients, having different number of samples that we have already seen. Okay? So which are called label distribution skew, and then feature distribution skew, and then quantity distribution skew. So this basically defines the notion of heterogeneity when it comes to data. So as we have to handle high level of heterogeneity, and Fed average is not going to be the right solution all the time. This is something not so relevant. I'll just skip them, and then I'll go to my other slide where I'm going to focus completely on different aggregation mechanisms. So the reason why we need to explore various aggregation mechanisms is that, right? So how can we handle the statistical heterogeneity that is seen, across client, with respect to data that each client handles? And again, what kind of threads that are for clients? Because if the client is a mobile phone, it will have its own kinds of threads. Because mobile phone is prone, to probably some number of threads, while drones, which are participating in federated learning, will have different threads. And then again, when it comes to security issues, right? Different devices will have different issues when it comes to sort of attacks, right? And again, what is the level of personalization that we wanted to achieve? Because how attention should be given to each client? Because simply if we use a Fed average mechanism, what happens? All the clients are treated equally. Okay? So that is something that we do not want. especially when it comes to healthcare setting, the learning that happens in, let's say, a hospital located in state headquarters should be given more priority. So as it will have more of no more of samples, and then it will be so it will be having more number of samples, and moreover, it will also have high level of diversity across patients visiting hospital, and then the number of diagnostic tests being taken for the sake of patients are going to be extremely high. Okay, so such kind of participating clients should be treated better, should be treated differently than the other less or non-participating clients. Okay, let's say there is a primary healthcare center where the contribution is very less, so that must be treated less compared to the other entities which are there. So depends on the way how clients are treated, no, separately. So based on all these factors, and answer to all these factors are not certainly the Fed average. Fed average do not address all these challenges. Okay, because as we have observed in the previous evaluation curve, so Fed average works well when only when data are following IID format, right? When it is non-IID, then we could see that there is a drastic decline in the performance when we use Fed average. Okay, we just keep this Fed average as our baseline, and then we are going to see some algorithms, and then we are going to observe how they are better compared to Fed average. So here is the standard implementation of the Fed average, which we have already seen before. And next, besides all the heterogeneity that we observe here in terms of data, statistical data heterogeneity, and then how weak each clients are, or how good each clients are, what level of personalization that we need to preserve. So accordingly, all these factors, yes, Fed average is not going to deal with all such factors. Besides that, more technically, so we have a problem called client drift, because not all clients are equally same, and we do observe something called client drift that is usually caused by this non-IID distribution of data. Okay, for example, as you can see here from the diagram, sorry, so I'll not be able to use my pen here, but let me just I think I just follow my cursor so that
Yes, sir.
you'll be
Yes,
able,
sir.
yeah, you'll be
Yes,
able
sir.
to
We
at
can
least.
able. Yes, sir.
Thank you. Thank you.
Yes.
Okay. So assume that as you see in this figure, it is a contour. So we call it error plot or error map. For example, by considering it is visualized in 2D manner here, because where only uh, probably two weights are involved here. So x and y axis, x and y axis here. And then we take probably a range of values for a parameter, and then we plot this curve. So as you can observe, at the server side, we have no data, but data are basically located at client side. So clients will have probably different set of data now, so that in case you plot this contour, in case you plot this error surface, an error surface will mostly look like a kind of a fabric. If you just keep a fabric somewhere, and you would see there is some ups and downs, right? That's how the error surface will look like. And since it is a minimization problem, we wanted to find out the region where the depth is high, right? That is the region where we wanted to arrive at. Okay, so now we really do not know where is that global minima is, right? So every client will try to drag the gradient towards its own local minima, right? Because even at every client we have different data distribution, and based on data that we have, we would certainly have a different error surface, and that error surface is what actually seen in terms of contour map, as you seen here, right? As you can see here, probably this is the deep, or this is the ideal sweet spot that we wanted to arrive at ideally. But what will happen due to this local client or local minima that could be seen in local data. So what would happen? The local training will always be moving towards local minima. So now, what if local minima that are observed in different clients are not close to the global minima? Okay, so the client one will be dragging all the derivatives of the gradient towards the local minima. As you can see here, there are three clients shown here: orange, red, and then green. And so each one of them are actually moving completely towards very much away from the global minima, which is light blue here, right? So that is something called as client drift. So this is something that we need to control. Okay? So we must have a proper boundary or for the limit for the gradient direction that is realized at every client. So, in brief, and this is what called as client drift. Because client will be so much, it won't, right? Because client has no, there is no communication that we see as per the federated learning setting. Client do not communicate with each other. So client one do not know what are the data distribution at client two. Client two do not know what are the distributions of other clients participating in this setting. So that client will be independent and client will always try to drag the derivative to its local minimum. Okay? And the problem here is what if that local minima is not close to global minima? That is what is client drift all about. Okay, now, so in order to address this problem, and there is an algorithm called FedProx. Okay? So it is going to consider the notion of proximal regularization. As you can see here, we are not interested in just minimizing this local loss alone, local loss, right? There are k clients in the setting, and then we care about minimizing the local loss. So besides that, we also try to minimize this proximal term. So which is also a kind of norm that we consider. It is an extra factor that is dependent on weight values involved in the model. Okay? So W stands for the weight, global weight, and then WT stands for the local weight. Okay, because W is something which is obtained after aggregation, and WT is something that is seen at every client. Okay, now this proximal term here, so mathematically it is shown as norm here, but the actual meaning of this proximal term is actually explained here via visualization. And you are basically restricting the boundary for all the local weight updates, which means though local model can see its local minima, and it will not have freedom to move towards local minima, because that is not something that is our target. Our target is to drag the loss all the way to the global minima and not to the local minima. So in order to avoid this, we don't give enough of flexibility to local model update, and we just restrict the boundary. We restrict the boundary to this dotted circle here, so that the though client has a local minima which is somewhere beyond this boundary, but still client will be restricted only to move within this boundary, and client cannot move beyond this boundary, which means we impose some constraint on weight updates that client can contribute. Okay, though client is aware of its local minima, we don't allow you to move towards local minima, because that local minima will not be equal to or will not be even close to the global minima, right? So we wanted to restrict the model update that each client is contributing. Okay, so you may think that okay, this restriction would probably result in increasing the number of rounds that we need to perform in federated setting. Of course, because what we wanted, even in standard machine learning or deep neural network training, we always desire to have learning as slower as possible but consistent. For example, that is the reason why we keep learning rate eta always small. Right? So same way, by defining this boundary, probably we may have to do many rounds of training in a federated setting, but at least we would be able to address the problem of client drift to some extent. So again, when this mu value is 0, if it is 0, then it will act. Okay, this entire thing will this proximal term will become 0 in that case. If mu becomes 0, because mu is something that we need to learn. If mu becomes 0, then this entire term will become 0. So that what's remaining here is the local loss. So which is nothing but your standard classic Fed average algorithm. And as long as this mu is non-zero, then we do consider some weightage to this proximal term, and that proximal term defines the boundary within which client derivatives, the gradients that each client contributing can move around. Okay? And now we need to ensure that this boundary should cover the global minima so that your client, the gradient movement is restricted only to this boundary so that we are around global minima. So at one point in time, maybe after some rounds of operations, and we'll be able to reach the global minima eventually. So that is the idea behind this Fred prox, and to some extent, it is able to address the client drift issue that is seen prevalently in Fred average algorithm. So I'm just left with only a few minutes, probably less than 10 minutes.
Yes,
I'll try to cover a couple of more other algorithms, and then I'll take up questions if you have. The next technique for aggregation is that scaffold. So scaffold, it is a paper published in 2020, a stochastic controlled averaging for federated learning. So it is an aggregation mechanism. So this algorithm, actually, this approach, tries to change the direction of the local gradient towards the global minima. So it employs something called as control variate. So control variate C is going to actually change the direction of the gradient of each client. For example, just observe this visualization here. So now the global model is actually the gradient of the gradient of the global model is actually moving towards this direction, which means a global model knows that only when gradient moves towards this direction, then it will be able to reach the global minimum, right? Now, one of the participating clients K is actually dragging or moving the gradient towards this direction, shown in the orange arrowhead here. Okay, so this is something that the distance between these two is very huge. Okay, so that is what we are measuring here. So the distance between these two is very large, right? Which means these two directions are completely different from each other. So now we estimate this gap, and then accordingly the algorithm ensures that the gradient of this local client do not move towards this direction, but to the direction which is which the global model is doing. Okay? So it is just changing the direction of the gradient at client K, not towards this, because in case if we don't have this restriction, if we don't assess this control variate, it will be keep on moving towards this direction. But in case if it moves towards this direction, it is not going to be close to, it's not going to be near to global minima. So that's why we are deliberately changing the direction of this local gradient towards this. So this is something called as corrected update. So this correction happens based on this cross the control variate that is observed between global gradient direction and the local gradient direction. Maybe after this time, probably we would once again measure this control variate, and then if we are okay that okay, so the client gradient as well as global client gradient is also moving towards the global minima, then probably this distance would be less in that case, so that there is no much change required in the direction of the gradient. Okay, so the the change in the direction of the gradient actually determined by this control variate in case of this scaffold mechanism. Right. So when it comes to the problem of client drift, yes, to some extent it is addressed, but on the other hand, the number of uploads, okay, the number of uploads are going to be twice as compared to federated average. Okay, it needs to even remember a lot of information about client across the rounds, so that it would be a little bit heavyweight compared to Fed average, but at least it is able to address this client drift issue. And then we have this Fed Nova, where we are going to basically normalize local updates. Okay, don't take updates of local clients as it is. Just consider a kind of normalized factor, because as clients are following non-IID principle, because data seen in clients are non-IID following non-IID. So now every client must be treated differently, right? So instead of accepting updates from client as it is, we just apply some notion of normalization on all the client updates, and then it is taken for aggregation. So that is proposed in this Fed Nova. And then we have one more algorithm in this respect, that is Fed optimizer, yeah, which means adaptive federated optimization, in which it's quite different from rest of the algorithms we have seen earlier. So in all the algorithms we have seen earlier, mostly the work is being done at the client side, while the adaptive federated optimization mechanism. So we do some optimization being applied at the server side itself. Okay, which means, as you can see here, it is very similar. Whatever mathematical formulation given here, it is about Adam optimizer that we predominantly seen in deep neural network, right? Adam is a very popular optimizer for learning parameters for the network. Right. So here we are actually using two different history. So one is empty. It is one history where we are actually looking at for example, I can put forth an example here, a kind of analogy here, so as to make you understand what is this history all about. For example, you want to go from one place to another place, but you do not know the path to reach the place. So which means you decide to inquire at every checkpoint, and then you wanted to confirm whether the direction in which you are moving towards target is correct. And now let's say you go to first checkpoint and then you inquire, and this is the place I want to go, and someone is guiding you that move in this direction. So that you then again go towards that direction, and then you go to the next checkpoint, and then you ask someone whether, to confirm whether you are moving in the right direction. So second person also guides you that you are in the right direction. So what can you now confirm? Yes, you are in the right direction. So nothing wrong in increasing your acceleration, right? So now your gradient acceleration will be increased. Now earlier you were just traveling at the speed of, let's say, 30 kilometers per hour. And now once you are sure about your direction of movement towards target, you can now increase your acceleration or increase your momentum, right? Because we know that Adam is basically the combination of momentum-based gradient descent, no, plus RMS prop, right? These two are other variants of optimizers, and this Adam is basically the combination of both of them. So both of them looks at this history information differently, and the combination of these two is what called Adam. And when we use this Adam in federated setting, then it is called Fed Adam updater. So it is no different from Adam optimization algorithm as it is. Okay, so we just make use of this history information. So server, we are going to assess what is the direction with which all the gradients are moving. So in case if server is confident that all the gradient directions are towards global minima, then server will increase or give more importance to that feedback, and then it will run it will ensure that the learning happens faster, which means the momentum is faster towards the global minimum. So, and thus it will to some extent ensure that the number of rounds are probably less, because if we could, if the algorithm works in a desirable way, then we would be converging with right set of parameters in less rounds of operation. So that is the core idea behind this Fed optimization. So there are many more algorithms to follow. We have seen some standard or state of the art. Most of the papers, if you see, they are all published published between 2019, 2021, 22. These are all the state of the art aggregation mechanisms that are prevalently used in the context of federated learning. So with this, I'll stop here, and then I'll invite questions if any you have.
Yes, sir, yes. Sir, so now we will open the floor for query session, sir, from participant side. Yeah, dear participants, if you have any questions or clarification, please unmute yourself and raise your queries. So sir is here with us to clarify our doubts. Please, having any queries from participant side?
Hello, sir. Good morning.
Yeah,
Yes, I can hear.
yes.
Sir, is there any machine learning algorithms specifically better for classification of data?
Uh, no, your question is about uh, better machine learning algorithms for classification tasks.
Yes, sir.
No, most of the choices of machine learning algorithms we have for classification, yeah, most of the algorithms we have under machine learning are for classification. Right, as practically speaking, the most of the problems seen, most of the machine learning oriented problems seen in various application domains are all classification, which means we do have labeled data. So there is the I cannot
Actually, I have
say.
a database.
Okay,
Sorry, sir. I have a database for image database in the form of data Excel.
okay,
So
image
we
data
scanned the
in.
images in the form of Excel, CSV format.
Okay. No,
So
mostly
to use
uh, in case you are dealing with image data, we have popular CNN architecture, right? That should work best for your setting. But again, no, there is no single algorithm that would work best for your data. And when it comes to machine learning, you will have to experiment at least with 8 to 10 different algorithms. And then you can choose the one which is working best for you, and then you can take it for customization, improvement. Then you can realize, how it is working on your data set. Yeah, of course, I can have an idea if I look at your data set.
okay, sure, sure. Can I contact you, sir?
Yeah, certainly you can. Yes.
Okay, thank you, sir.
Yes, ma'am. Thank you, ma'am. Any other having doubt? The remaining participants having any doubt? Yes, thank you, sir. Thank you for your clarification. So thank you so much, sir, for your highly informative and insightful session on advanced federated aggregation algorithms. Your presentation provided us with a clear understanding of advanced federated learning concepts and offered valuable insights into the largest aggregation techniques and their practical significance. The way you explained these complex concepts with clarity and depth made this session highly engaging and beneficial for all of us. We sincerely appreciate your continued support in this faculty development program. Following the day before yesterday's enlightening session on foundations of distributed and federated learning, today's session has further strengthened our understanding of this important research domain. Your expertise, valuable knowledge sharing, and dedication to advancing research in artificial intelligence and federated learning are truly inspiring to all the participants. On behalf of the organizing team and all the participants, I extend our heartfelt gratitude to you, sir, for taking the time from your busy schedule to be with us and for delivering such an excellent session. Thank you once again, sir. It was truly an honor to have you with us. Thank you so much, sir.
Thank you, madam, for having me here. And
Yes,
once
sir.
again, I thank the management of the institute for
Yes, sir.
having me as part of this program, and my best wishes to all the participants. So thank you
Thank you,
all.
sir. Thank you, sir.
Thank
Thank you so much for this. Dear participants, we will now have a break for 20 minutes. I kindly request everyone to rejoin the meeting by 10:55 a.m. as because our next session will begin promptly at 11 a.m. And also request all the participants to kindly submit your feedback form without file. Or at the end of this session, we have posted our feedback link in chat box. So kindly submit the form. You need to maintain your attendance percentage at least 80. Then only you can receive a participation certificate. Thank you so much. Dear participants, welcome back to the second session of today's faculty development program. I hope you found the previous session insightful and informative. We are happy to have your continued participation, and I'm sure that this session will also be highly beneficial for everyone. Now, it is my pleasure to introduce our distinguished resource person for this session, Mr. M.P. Jagadishan, sir. Mr. Jagadishan is a subject matter expert and corporate trainer with over 23 years of experience in the IT industry, including more than 15 years of expertise in technical training and capability development. He is currently associated with L&T Edutech, where he plays a vital role in designing enterprise learning solutions, developing innovative curriculum frameworks, and delivering impactful training programs in emerging technologies. He possesses extensive expertise in full stack development, cloud computing, data science, artificial intelligence, machine learning, and enterprise platforms. He is highly proficient in modern technologies such as .NET Core, Azure, AWS, Angular, React.js, Node.js, and Python, and has made significant contributions in advanced areas including deep learning, DevOps, and cloud optimization. Mr. Jagadishan has trained more than 4,000 corporate professionals and guided over 50,000 students globally, helping bridging the gap between academic learning and industry expectations. His association with reputed organizations such as Hannibal, Virtusa, Aspire Systems, and LTN Mindtree reflects his strong industry presence and technical excellence. He holds an ME in Computer Science and Engineering and has earned several prestigious certifications, including Microsoft Azure, AWS Educator, Salesforce, and ServiceNow credentials. His achievements have been recognized through notable honors such as L&T Edutech GEM Award and the ICT-ACT Best Trainer Award. Today, he will be delivering an insightful session on building a federated learning pipeline, a highly relevant topic that explores the intersection of distributed machine learning and modern intelligence systems. Please join me in extending a warm welcome to Mr. Jagadishan for today's session. Sir, we are delighted to have you with us and look forward to your valuable insights. Now, I request Mr. Jagadishan to kindly take over the session. Please, sir.
Thank you for this. So the voice is audible.
Yes, sir. Yes, sir. You're audible, sir.
Thank you for this introduction, and we'll start the session.
Thank you so much, sir. Yes, sir.
So maybe I just go on mute on video. I'll make it audio on. Yeah. So we'll start with a few questions, especially from building a federated learning pipeline. Of course, it's one of the new method that we have. I hope the screen is shared to everybody. Can I get yes, no? So
yes, sir. We can receive it.
This is it.
Yes,
Right.
yes.
Because I'm just being in other screens, so I just wanted to know whether it is shared or not.
Yes.
Yeah. So now, I can I get some answers from the participants? Like, so what are the learning methods in AI is there? And so I guess most of you are been aware with the learning methods, like in AI especially. So we have experience learning, machine learning, deep learning, of course, reinforcement learning. We have a lot of learning methods are there, and every learning method has got its own unique sense of understanding and the contributions in development of AI. And so, may I just know what are the learning methods? Maybe what I've it is few learning methods. Can I get something from your people? Like, what are the other learning methods that we have? And so from that we can start. Anyone? At least you can text it in the chat, so that from that I'll take. Nobody's there. Okay, so I guess we'll just continue with my understanding of and also small research that we have done. I know the predominantly we use machine learning and deep learning, And if you see in that way, we have a, maybe we'll start with the challenges in that learning methods. Let's say machine learning, especially. Of course, deep learning has got right now it has been transferred, or in Gen I we use what you can call transformers, where we call BERT method and GPT methods are used. But generally, what this learning method is doing, and especially machine learning methods. So the challenges are one is the security in data. Of course, we follow GDPR and HIPAA privacy policies. Of course, you know GDPR is a general governance of data protection policy that is followed from the European countries, and HIPAA is followed for the US health insurance. But in this both this data protection, maybe in India also we follow the same. Maybe in fact, if we see in India, the data protections are done, especially on right now we have our own policy named called Maharaj Cloud Policy, Maharaj Cloud AI policy. Maybe if you go and search in Google also, you will be getting that. It's somewhere sometime down the line from here, 10 years before Government of India, then Ministry of Information and Technology, they formed this policy. In fact, these policies are been amended every now and then, and so on. Now, you can have a question straight away why we talk about the security of data and so on. Now, see, in today's world, if you see the biggest threat or the biggest an AI world, protection of data. Maybe the people are saying that we protect the data, but are the data are protected? Are the data are being kept in a good way? Definitely, it's not. And because we have the biggest challenge is collecting the data and keeping to abundant of regulations and so on. And also not, we are not getting maybe already we know that this ChatGPT and maybe Gemini, Cloud, all these LLM models are either generating the data or accumulating or getting the data. So as the AI models are growing more and more larger and larger, we have very big challenge here is that how I'm going to protect this data, how I'm going to protect this data. That is number one. And number two is keeping all this data in one place and probably in some data centers. So when you take Azure and AWS and Google, the three the major players in data centers, everybody has got 60 plus 70 region of data centers are there across the globe. But still, if one is fails and the other will go, and maybe we may have the problems here in data center too. Having too much of data and too much of depending on data center, probably it also makes problem. It will be a challenge for us. So that's what I've just given the challenges that today's centralized intelligence, today's centralized AI has it's been in the challenges that we are facing. So if you see in this single point of failure, yeah, of course that's can be happen. Protecting the data and without any issues, without the legal and compliances governance to the respective the country and the region, and also keeping the data and getting every time the data and trying to build the model better and better. Is it possible to do for everything? Especially there are certain data are there. Let's say finance data of a country, health data of of an individual person, or in a share market, very transactional data of the country or of the company. So there are certain data are there, or that's what I put as bottom. Uh, One is traffic, and another one is the silos and privacy of data. So one is I cannot take two. Is I got the data, so I cannot get it everything. Say for example, I have a chat GPT, so I'll put everything, I'll generate everything, I'll give a lot of data. No, that is also not good way. But what we are going to do for this? Of course, there is another point is latency. if I keep everything on centralized process, is that it's going to work for us? Say, okay, I'll keep all my data in data center. Let's say a patient data of a health, or let's say finance data of a bank. Okay, that is not possible. So now recently Claude has came with the new model called Claude Asian banking system. That may be agents. It means that it can run a bank by itself. A Claude can run entire bank by itself. Of course, in India, recently the government of India, Ministry of Finance, there is Minister of Finance, she was being talked with the fellow members that with RBI governor and all. Is that how we are going to face this cloud banking system or autonomous banking system? And maybe they are starting measuring. Of course, in India we are not allowed that particular thing, but still, if it comes in either way, then we have to see the measurement. So in this all these cases, how I'm going to manage. Okay. So that's what the traditional way of machine learning, especially machine learning and deep learning, we move all the data to the central server. We train the model, right? We train the model. So the risk is to protect the data, or to make data to be very legacy of transferring the data and so on. Now, of course, the last one, the compliance, is trying to keep how much I'm going to keep in a bit of compliances. For all these things, we have some solutions. Of course, it's not started now. It was started from the concept of distributed intelligence, right? Of course, maybe the past 2 days, you might heard about all these concepts from other, professors and probably the corporate people. Uh, I'm just coming on my way. In fact, it was like when I was doing research, or when we are trying to create a proof of concept for a defense company. I don't want to reveal that. It's a defense company, and I'll tell you the scenario, and from there I'll tell you how I started federation learning and the importance of federation learning. I'm just saying the scenario. So it's a defense company, and it's one of the major defense company in the world and in India. So they cannot reveal all the data. They cannot reveal the data just like that, and because the data is involved. 1 minute. The data is involved with. It's involved with secret of government. It's involved with the secrets of you know. It's involved with the entire country of people. So once the data has been taken to the centralized model for AI, then AI can train, and it can give answers for the defense to different for the defense organization. That's not a problem. Now the problem is they said, listen, Jagdish, I cannot give the data to the model. Now what I can do for that? I said, maybe in those times I said machine learning. Hey, we can use machine learning. You cut short the data and give to me, and you whatever the parameters of data it seems to be. Um, in a topic of feature engineering, I told them you cut short some of the data, whichever it is not. You will take highest mandatory data to train the model and so. Actually, it was like I'll tell you, like finding out the mysteries objects that flies in the line of control, that is in border of the country. The mystery objects like drones or something like that. Now for that they have so many devices, from satellite, from RFD, from radio frequency data, and from ground station BST uh, data. So many data they have, radars data, and so many data. But slowly, when we have, I'm just telling this is some happened some years before. So that then we have started doing some kind of other options and so on. But we came to one concept from blockchain, and then we have jumped into centralized, decentralized, or what you can say, distributed intelligence. So I won't keep data in local. At the same time, I want to make it to be a model better. So then we started going to this exploration of federation learning, and that was given solutions to us. I'm just saying the scenario. In a very simple way, the data is kept in local and the model is alone taken. So that's all. This is the solution we have arrived in this particular for the particular problem. So this is the scenario for me as pushed to enter into federation learning for developing a proof of concepts in a real-time entity. So this is after this I cannot reveal too much because it involves a lot of confidentiality and so many things. But I'm just telling the overall gist of the model and how it works and how federations used. Okay, so now let's go and see the origin of this federation learning. So as I told you, I'm just narrating that as the data protection and silence of data privacy. For all these things we have started. Okay, so in a way that the centralized learning processing has been created over the period. Of course, it started from before cloud and before grid computing, cloud and so on. Because cloud has given the process of it's keep your data some way. You move the data whenever you want or something like that. So from there, we have started to go to the distributed intelligence. So in distributed intelligence, we decentralize the consultation of process. It means that edge computing has been taken away. Edge computing and edge devices has taken place vital role. A mobile, IoT devices, or any small devices will start generating the data, and it keeps the data to that level, and that data will be collaborated to the centralized system. Centralized system will give decisions to the data. It's like we ML model, we move all the data to the model, but distributed and federated model is given an option of it's given an option of moving model to data. So the edge computing edge devices, the data also kept in and around of in the same devices. It has moved the data. So for example, I'll tell you, maybe in mobile, everybody uses Android nowadays, I guess. And we have the Android mobiles or maybe iPhone. I'm not taking here, but in this, if you see, you have in a keyboard, in a WhatsApp or in a keyboard, you might seen when you type a message. Yeah, when you type a message, maybe I'll just show you. We will be getting here the intelligence. Like when you type, probably we'll get some recommended words. Now the question is, it means whatever I type, based on that you will get a recommendation. Maybe you might seen this when you type a Gmail ID. For example, for me, I type JE. Immediately I get my Gmail ID and my company mail ID. Now the question is that your mobile is recording all this data? No. Or you can have another question that said my mobile is taking all my data to somewhere? No. It will take the pattern alone. It will not take the data. So that is the one of the good example of decentralized consultations and federation learning. It means the data will be there. The model will come and work for you for correcting the grammars and correcting the spellings or correcting the reason words that you collecting the reason words that you have used. So the model, it comes to you. You will not approach the model. So that's the point here. So maybe I'm just discussing. Now let's go a little deeper to understand this federation. What is this federation model, and so and maybe the time constraint. I'm moving a little faster, so please don't get into thing like okay. So of course, maybe if I want to say that the paradigm shift has happened uh, to the distributed intelligence, and from there it is federal learning is. So the very important thing is not sharing your core data to the model. The model will get, it will come and work for the data. So the devices and computes mathematically updates. It means that the devices will get the mathematical updates. Let's say using Grammarly application, right? It means that your grammar is corrected. When you type something on your ChatGPT or in Google search engine or in your mobile, you enable Grammarly. You think that the grammar is doing it? No, it's some mathematics is there. Some algorithms is working. So the devices will get that algorithm. The devices will get the mathematical one, and based on the combinations of all that, it's converted to the transformation of words and English, and it's connected. So in fact, it protects the private data and it leads to the local environment. It is not taking out of the bond. So uh, in a way that your architecture protects, the very important thing is protects the data, but it enables a collaborative intelligence from across various places. Let's say the example I said, Grammarly, and maybe other things. I'll tell you traffic data of Google Maps. You think that your data have been taken completely? Of course, when Google has started initially, they are consuming your data. Now, what they are doing is they bring the model and they see your data, and accordingly, it will tell you to a GPS location. Here, what is happening? Is the traffic is there in your road, or if the traffic is not there? So it's something. If you want to tell you here, in a traditional way, we the data will approach the models, and the model will train, and the answers will be given to you. In federated learning, it's an opposite that the, the model will, or the intelligence or the algorithm or the mathematical computations will come to the data, and the data will start executing accordingly. It means that maybe we can say another way, uh, in a very simple narrative. I go for the restaurant to take food. That's what it was happening. Now the restaurant food is coming to me when I order. So maybe it's not a right analogy. I'm just telling you in other way. So that's what it's all about. Maybe if you want to put a simple words, little more, what is a federated learning? Of course, so many people have discussed. I guess I don't want to discuss too much on this. I'll just go to the pipeline very fast. So, and a machine learning method with a collaborative model with raw data, but never leaves your local devices. So in a age start, every data and model will be trained. The intelligence will be created in your device itself. So the data and the model will be there. It creates intelligence, and what it will take is it will take only the model. It will not take the data. Again, I'm repeating. It's not only the parameters. The two important parameters will be taken. One is the weight and gradient. So I'm not able to understand. Can I get a simple analogies? So I have just created some analogies in understanding this federal learning. So for example, there is a master chef, and you want to create some, the recipe or some master recipe of, say, for example, XYZ food. Now, what he can do is he can collect a recipe, the same recipe how is done from X hotel, Y hotel, and Z hotel, or X chef or Y chef or Z chef. So he can collect he can collect all the methods and everything. He can bring only the feedbacks and the strategies which is approached by the chef. I don't want the name of the person. So, and I don't want what they are, which company it is, or something like that. So we bring everything and we will put together and we'll create a master recipe. It's one example we can say. Or say, for example, improving maybe improving the for example, the understanding of customer feedbacks. Now, when not normally when you ask customer feedback, and any customer supply chain management or any B2C environment, customers say, I will not give my name and Aadhaar number and phone number, but I'll give your. Absolutely fine. We don't want your name, we don't want your Aadhaar number or phone number, and so and so. Because if you see now, when you go to the small grocery shop or restaurants, or maybe especially on these all grocery shops, so tell me your mobile. Sometimes we hesitate to give mobile number. Because once we give a mobile number, they'll take our name and mobile number. They'll go and sell this, and somewhere the bank people or these XYZ companies, they'll offer the marketing, which we annoy ourselves. Just now when it's happening to me when I was taking a session. So for that, what we can do is, I don't want your name and phone number. You give me your feedback. Or it's okay. You collect customer details, everything, along with the feedback, just for that. Well, the other way, the customers, I'll give my name and phone number, my feedback. It's okay. Either the way, it's okay. Now, we will collect all the feedbacks from the respective domain of B2C, whether it's a grocery or it's a retail, maybe a showroom, a bike showroom or a car showroom. We'll collect all the data. Now, we'll collect only the feedbacks and suggestions. And that feedback and suggestions are compressed together, and we will see which is very good, which is got changeable, or which is better, something like that. We will take all that and collectively we make as one, and from that we will make it as a master feedback and suggestions. From that we will go. So that's what. So the branches will have their own data, and the more it also trains. We will make feedback as a collective one. That's a model. We'll collect the data and we will have we will collect 100 people. From 100 people, we'll have 100 customer feedbacks and suggestions. From that, we will create a consolidate of 10 or 15 minutes from first showroom, then for second showroom, third, four, five, like that. Now, all the 10 feedbacks from each and every showroom will collect and will make finally 10. Okay, so that's how we will make. We will not consider everything, right? It means that is highly impossible. It's highly inhuman, or it's not machine level also. It's just like collecting the hallucinations of data or anomalies. Probably it will not make a sense. So, and that's how we can make it. So, in fact, that is what it does. Now, what is the weight here and gradients? Weight is the result. Say, if this is x1 and x2 and x3 is happening, and this is what the y1 for me, that's weight it is going to. If this is going to be the changes, the inputs, and this is the final weight, I can see. And the gradients are, we have a lot of gradient in a deep learning model when we use ENM and RNN, all these convolution neural methods, we have gradients, stochastic gradients, and optimizers. Maybe we call the most gradient descent. Lot of optimizers are there. So in fact, we use gradient descent. It means that trying to get the best of the given changes. So for example, between 0 to 1, what I can get the best. Okay, between 0 to 0.1, what is the best? If it is a weight is 0.1, from 0 to 0.1, what is the best changes that I can make? So trying to get the best parameter of weights and gradients based on the accuracy results that we get. Based on the accuracy result, and we are going to get. Of course, we have discussed this also little much. Right. So the physical architecture of any federal learning, it will be like this. You know, um, 1 minute. So it's like it will be having a response of client selection, aggregation, and orchestration. It means that the clients, the device, every devices will produce the data with the trained model, and it connects and it put. I'm just talking the overall architecture. Then we'll go for the pipeline, and it communicates in terms of weights and gradients. It transfers and it encrypts, and then finally we'll get it into a centralized model, and we'll keep that. And the centralized models are used in predominantly for overall process too. Okay. either, for example, image classifiers. Right now, most of the LLM models, they use federal learning methods for training, especially on generative adversarial networks, like generating, you got images from Gemini, Claude, and ChatGPT and Sora and so on. How you are getting these images? Your images are generating to you. It seems to be very nice. It seems to be very accurate. How the images are generated? It means from the learned model, whatever the data we have given, from that it's learned. It's got the weight, and from that weight, it started created a centralized weights and gradient descents and all that metadata combined together. Based on that, when you ask certain image, generate an image of car, so it generates a beautiful car image. So based on previously trained model, locally trained model, based on that it will get. Okay. So in fact, I know because I've done little research in GAN with federal learning. I know it was a wonderful method, like GAN was updated. But I know you might have a question. Sir, do you think that absolutely the data is not leaked? Actually, if you ask me honestly, no, it is leaking. We'll discuss that. We'll discuss that. What are the parameters that when I'm creating this architecture, what are the things I want to take? Maybe the same thing I put it in another way. So let's go into the model, federal learning pipelining model, yeah, the architecture or you know uh, how it works. Okay. Maybe any doubts in this after this? Any doubts? Maybe I'm just running in my PPT. Uh, yeah, maybe the content is heavy, and just I wanted to go a little faster. Is that fine? Maybe I'll just yeah.
Yes, I can
Any
proceed.
yeah. Okay. Yeah. So maybe
So
if any doubts there,
dear
you please.
participants, yeah, if you have any doubts, please ask.
Yeah,
Yes,
maybe you can put a question too.
yeah, you can
So maybe
also, if suppose you're having any doubt, means you can also put your doubt on chat box
yeah.
or
Maybe
directly you can,
I'll
yeah,
take that later also.
yes,
Okay.
yes, you
Okay,
can.
so let's go into the core, and so maybe now what we have seen, I'll just summarize it and summarize it. So we have seen the understanding. Of course, I know there is a repetition of content because every individual comes here for an hour or 2 hours. We come and narrate. Maybe certain times it can be a silo of same kind of things. You find something a neutral of what it is happening. But let's go into the little for my very important core content of creating a pipelines and doing something on that. Okay. So the first and the core content is um, the server is initialized a global model. That is not a problem. But we will make it we will make it the first level of client level. So we will start from the the IoT devices which is connected or IoT. So I'm just saying why IoT devices. It could be an IoT device. It's not only the mobile. It can be a sensorical. It can be a mobile data or from laptop or from data centers too. It's not that always these small edge is alone is contributing for the centralized federal learning methods. Everywhere it contributes. So the server creates a base model, like maybe they use convolution neural networks or neural networks, probably DC GAN, decoupling convolution neural network, GAN, generative adversarial network, or RNN, LSTM, any maybe transformers too. Transformers are using it. So it identifies the fundamental infra level connectivities, whether it is all connected properly, and so and all. Now, once it does identifies that infrastructure, so the meaning is it finds out what I can keep as a centralized model, and it connects via various networks and infra. It makes sure that the infra and the networks are connected properly. And the very important thing is the model which is transferring the model weights and parameters. Is it all secured models? So that's what I've given a gray and a blue. If it is not secured model, that is, it is distributing the model. it is distributing the model. If the distributed model is not secure, if it is not secure, or if it has got some some threat or violation, so the centralized server will not admit that particular network, or it not that particular, it will not allow that particular devices to connect. So it's what gray and clear. The blue which I said here is it connects it. It connects it once the network is secure, the infra is okay, and it can initialize the model and transferring. That's what I said. The initial model is broadcasting securely to the secure from selected edge devices. Not I see. I'll connect thousands of millions of edge devices across the globe. I'll collect the data. I'll put it in centralized server without any protection. Then you will be in the biggest trouble. That cannot happen. That cannot happen. So if it is happening, then the server will be in the distance. Maybe it will be the risk, and it will be against to the compliances and governance. And to avoid that, we will create this firewall structure, and then we'll go. So the next one, the next very important one is we go and see here that we are going to receive the global models from each device trains locally. So the model learns from the local data that we know already. I've told you that it is happens. That's how the federal learning is going to happen. So the three important things and that it generates. One is the gradients. I already told you. The third one is weights, and it also generates the local parameters. Now, sorry, you told it's only a weight and gradient. Now, why we are discussing about the local parameters? It's not that it will not take the data. It will try to take certain parameters, like how many epichoice that neural network was run. So, what is the minimum losses, or what is done? Say, for example, let's say GAN environment, generative adversarial networks. Each generative adversarial network is the generator and discriminator will run in parallel. So it means generator will generate the image with the perspective or loss method, and based on if it has got a two loss, it means that it's a fake image, and discriminator is winning. If discriminator has got too much of loss and generator has got very less, it means generator is winning and generator is generating the good fake image. So by the way, it will happen like up and down for every time that we do. So in that case, what happens is we will measure the loss. So that's what I told you. Again, I'm repeating. So it gets the parameters. It gets the parameters in terms of local devices, weight. Number two, the gradient distance, that is optimizes. Maybe instead of saying that is the gradient distance, we can say one of the very good terms optimizes, and that in fact that is a very good one. The optimizers will help us. It will be we can say that's a very ideal term to use also. So, and the third parameter, as I told you, the parameters of like losses, accuracy, and all other elements, all that other elements that we can take, and we can put it here actually. So that's what I mean here. So I guess you got it. What I'm telling you. Yeah. So the third one, or that is, so we will do here local training, the weights and the local loss, the gradients, and all these parameters will be taken. So when the parameters, of course, it represents in a weights, accuracy, loss, recall functions, and the gradient descent optimizer values, the best fit of values, everything. Okay, it is transferring everything. There is no problem for us now. Now, that is the rule is there. Let's say the privacy protection. That is, in a pipeline building, when you say federal learning pipeline building, transferring the data and getting the data from the model, it is not going to be a challenge for us. maybe just creating a simple protocols, FTP protocols or HTTP protocols, we can transfer the data maybe by simple Python connectivities with a centralized server. We can with protocol we can transfer the data. Now the biggest question is that how I'm going to bring the privacy for this privacy protection. Now the question is that why we talk about the privacy protection. It means that when you transfer the model, when you transfer the gradient designs, and when you transfer the parameters, probably somewhere, I'm telling you, somewhere, the data might be leaked. Now, I'll, I'll tell you, maybe if you go to ChatGPT also, they say we will protect your data. In enterprise version, they say we protect your data. Now, the question is how much they protect. And the reason one of the interview of OpenAI, maybe just they in the conversation they say that we can say it's 95%, the 5% probably along with the parameter the data might be leaked. Now the question, sir, you can give me an example for that. I'll just tell you. Let's say based on certain finance data, let's say finance data you do transfer. Now you're training the model based on the demographic. Like demographic is something from the location, the maybe the longitude and latitude, all that. Okay, you have some data, and from that financial data are there. So in this city, this much transactions are happening. This city, this much transactions are happening. Now from that, the city data is going. So from that, you can understand there is some kind of categorical in a form of categorical city location data. We are transferring the longitude and latitude data also, probably when it leaks along with the parameters. Let's say for example with the weight, that is also one of the weight, longitude and latitude. We are not giving a city name. Say for example I'm giving a city name, but the longitude and latitude is I've given, and along with that the data is going, this is a transaction of this particular city. What happened here is you transfer longitude and latitude along with the weight and gradient descent. It's more than enough to get somebody that, okay, oh, this city has got this much wealth and this city has got this much wealth. Probably I'm just telling you in a negative aspect. Okay, they can understand that plus and minus of the city, especially on finance. Now, when it comes to that level, then you are leaking the data. Now the question is, now how I can uh, differentiate or how I can create privacy. Now, any idea about this? Any one of you? Maybe maybe you people have been rigorously worked on this kind of things. Um, any interesting ideas that you can bring? Sir, I think we can do like this. We can do like this. Any ideas? So I'm just talking almost 40 minutes. I just want to see. Any maybe you can type it in a message also. Now, how we can protect this data? Anybody? In what way that I can do, and what's the way we have? So now immediate answers. Maybe I know you. The silence seems to be very low. I don't know whether it's my voice is read audible. Yeah. So the number one, you say it's in, sir, we can encrypt the data. That's what is shown in the slide too. That's the easiest way that you can see. So that's we call homomorphing of encryptions to the data, so to the model, to gradients, to weights, and everything. But I've given there is a DP that's we call differential privacy protection. It's called differential privacy protection. So what is that actually? Maybe I've kept it a separate slide. I'll go there and explain. I'll come back. So we call it as a differential. These are the mechanisms we use it in pipelines too. So how we are going to create the first one of the, so I've discussed here several mechanisms. The homomorphing encryption is allowing encryption method for all these models, allowing encryption methods for this gradient designs, so that when you say encryption, it will go encrypted and decrypted in centralized server. So the people are there to hack that encryption also. So it's okay, but it is not that much defining method. Now then, what is the differential privacy method that can be introduced in the? It can be introduced in this pipeline, federal pipeline methods. Say, for example, you have a data of. I'll say like this. I have a data. I'll just say like Ramesh has withdraw 5,000 amount from the ATM and he spent it 2,000 rupees. Say for example, XYZ is a person who withdraw 5,000 amount and he also spends 2,000 rupees. Say for example, this is a statement. It's a transaction. Now, in normal traditional model, when you train, of course, in a GAN model, in this FL model also, the Ramesh person will be there, and also the data will be. He has withdrawn for 5,000, and so Ramesh 5,000, spend 2,000. So Ramesh withdraw 5,000, spend 2,000. Some weights will be like this. The name is coming, and weight is. We need that amount. It's okay. Now, what we can do is differential privacy is mathematically or in a statistical way, we'll try to create noise over the data. Let's say instead of Ramesh, we'll just replace person. Instead of 5,000, I say 5 rupees. Instead of 2,000, I say 2. So X spends some X or Y is it spends 5 and withdraw 5 and spends 2. Now, when somebody was hacking this data, what is XYZ and what is 5 and what is 2? The 5 is 5,000 or 5 is 5 lakhs or 5 is 5 crores. Nobody knows it. So unless otherwise you decrypt and you tell to the people. So that's what we call DP FL pipelining method is. You create a noise, temporary noise over the data, and you mask so that's what we say, masking individual data contribution, reconstructions or something. But by masking that individual data, we will not take the original Ramesh data or 5,000 or 2,000. We'll try to get only the X5 and Y2. So Y is spent, X equal to 5 means it's something withdraw. Y equal to 2 is X is spent at Y. So something I'll say X equal to 5, Y equal to X and Y equal to 2. Now, seems to be a mathematical formula and nobody can get what it is. But we know X is a Ramesh, 5 is 5,000, Y is a spend, and that's why we say X equal to Y, and Y is, what is that Y value is 2. So then R is equal to 3. So the remaining withdrawn amount. So now, if you train this kind of model, when the model is also reliving the data, that data will be in a shielded method. So that's what we say differential privacy method is one of the method which is used in most of the most of the places too. And secure aggregations, we'll just discuss. So maybe we'll discuss again in a pipeline of security methods. So that's what I mean here, privacy protections. So that's how it's updated. Now, once you upload it and to the global server and centralized server, so what we have to, so we have created, we have trained it, we have secured, we are uploaded now. That's the fourth step. So now, what are the things we will do in this one? Okay. So the server now aggregates the updated received from the multiple clients. So from multiple node or multiple clients or multiple points, server will get server now start aggregating. It means it consolidates. So it consolidates in the two meanings. One is a Fed average, and we say list of the things. So Fed average is nothing but the most popular method. It creates a federal average, and for the consolidated data. That means for every model, it gives some consolidated. From all the consolidated, we'll try to combine together. We will try to create a consolidated, and then it's uploaded to the distribution models, and it goes maybe several iterations to do this process, and finally we will find out the right one. So the survey will combines with all the local data federated, and we call it as a federated averaging. So it will continue still it finds, yeah, it has done its best. So then it will stop. Unless otherwise it keeps getting some data, it will update, it will aggregate, and it creates better. So once it has reached the best point, and then it will start communicating to the rest of the world. So in fact, I've just given a little deeper formula for a federated average. So W is something the weight, the new weight model, and K is nothing but the clients, the number of clients, and NK is the client proportions. Say for example, what the data we have given, and the local weight is finding out the total weight. Based on that, we will start finding out the federal average. So federal average will give the overall average model. For example, M1, M2, M3, it has given average 0.1, another one is 0.2, and another one is 0.3. Now we'll take all the 0.1 plus 0.2 plus 0.3 divided by overall value 0.5. So that average 0.1 or 0.1.5, based on it, it will start. Okay, so this is the one which is done in federal model. So in fact, I've given the formula, but a little more deeper understanding I've given that. So 1 minute, I'll just take 1 minute break. So I guess you got an idea about the steps consolidated. I'll just summarize. So, but still something is there in security and also transmitting of data. We'll discuss that the challenges that we have and how we can mitigate that. So we get the data. In fact, we have followed the same for the defense, which I've told you, right? What we have taken is we have developed the models because we have a lot of devices. Lot of devices give a lot of data. We train the model in locally. We push the model into the encrypted format. We have used some new encryption methods, and that's what I told you, like DP, differential privacy method. We created unknown noises. So when you encrypt, when you decrypt also, if somebody is hacking, they don't know what actually. It seems to be a noise. But we transfer that to another model, and it will be based on the decrypted that noise, and again we're getting the original data and finding out the average federal average, and from federal average we'll find out the average of weight, average of gradient descent, average of parameters. So based on that, the parameters will be trained, and from that we will be doing this task for the rest of the things for the release or something like that. Okay. So in this we have some examples. Okay, I think you got some knowledge about pipelines, but before discussing still a little more challenges, okay, challenges discussion. Let us go and do something here, and like types of federal learning is available right now. Probably this is also discussed by some people. I want to discuss something a little deeper to federated transfer learning, which is something today's latest method. So horizontal federated learning is something each hospital. Say for example, I'll take hospitals A and hospital B. So in hospital A and B, you will have a data, and but you have a different uses of data. Hospital A will have some set of patient and the patient treatment and so, and hospital B will have a set of patients and their set of treatments and so. In fact, definitely this federated learning can be used for hospitals for for better treatments. Maybe in AI can do a magics in this federated learning, especially on healthcare. For example, you assume that some patient is there in a down city or somewhere in a South Tamil Nadu where it is maybe a little urban and little rural, and they don't have that much facility to treat something like that. But same thing is there in a little two urban and metropolitan cities. We have all the facilities. Say for example, now this metropolitan cities they don't want to reveal the patient data, the name or age or what, the phone number or other details. They can release the symptoms and how the symptoms are diagnosed and how after diagnosing how they predicted. They can release that data from all the hospital A and B. Now combined together, putting in a federal learning, you can create a predictive, it's a predictive health causes, so that now the model can be used in down south, say maybe it's a village or rural or semi-urban or something like that. They can go to the computer and they can search the symptoms and they can get it. So it's already there is one I forgot the name. I was using that. The app was there. Okay, I'll just remember and I'll tell you maybe after some time. There is an app is there for this diagnostic. Okay, so like that we can for that semi-urban or semi-rural, same treatment how they treat it. Maybe they may not have exposure. Now they can have exposure and they can see how we can do it just done in that hospital. It's not only vice versa. Sometimes this urban might deal something better when it compares to the bigger, the another hospital which is there in the pure urban. Okay, so this kind of things we can use it in, but maybe we have discussed the use case too. So, what is the vertical federal learning? It's something the different places, same users. Here, the same users and same features, and same features and same users but different features. It means that, for example, let's say A1, he has got a bank account. Same A1 will have insurance account. Same A1 is a person, he may have a legal account in bank. Same A1 person may have mutual fund details. So one person used in many different places. So in that kind of one, we can call federal learning, vertical federal learning. So what is this federated transfer learning? What is this federated transfer learning? Okay. So 1 minute, I'll just take a water and I'll come.
Yes, sure. Yes, sir. Yes.
So when you come to the federal transfer learning, completely the users and features are different. Say for example, I'm taking a model, building a model for let's say in automotive industry. Maybe I also worked to this automotive industries. The one industry, let's say the Maruti has got a different, the setup, the details, and something like that. Maybe we'll just go to the another one, like let's say Indian Mahindra or Tata. They have a different kind of organization, different approach of the model and of the data and building of models or approach of manufacturing itself. So for that we are creating an AI model, say for example for an automotive industries. Now what we'll have here is, I'll tell you one challenge here is, when you have a different model with the different users with the different features, and let's say feature is a different columns. Here we'll have a different column, here we'll have a different column. Maybe the manufacturing sector, what domain is same, but the representative, the columns are different. What I can do for this? I can build the model, but I'll tell you the challenge alone. The challenge is the more unbalanced form of data might you get, number one. But the transformation is only talks about the manufacturing. Both are manufacturing, but the approach is different. And you create the model, and you just send the model alone. You transfer the model alone, and the model will have it's about as overall about the organization X and Y. Say for example, I'll tell you one thing. A person is playing a cricket. A person is playing a football. The approach of cricket is totally different. The approach of football is totally different. But I want to put this person's in fitness knowledge. Okay, then the knowledge, fitness knowledge will be same, but only thing is the models will be different. So it's what we put here: horizontal and vertical one. Maybe I've just given a user. Horizontal is something. So for example, we take age, BP, and sugar. And banking is we do saving and transaction, same user, but in the same user when you go to the insurance, health policy, and claims. So the domains will keep changed to us. So that we call it as a vertical and horizontal. Okay. So as I told you, federal transfer learning, the hospital in India and hospital in US, definitely both are hospital, but the mechanism or the one which we use, right? It's totally different from the Indian hospital to an hospital which stays in USC. So that's where with the different medical demographics or the different testing capabilities, different challenges for day-to-day operations. By having all that, it creates federal tax and federal transfer learning. So it transfers whatever I learn and then I'll keep it. Okay. Now, as I told you, I'll just discuss in very fast. Um, as I told you, like we have a problem here. The problem is in security, the threat management. So, as I already told, differential privacy mechanism it creates an artificial mathematical noise or updates in existing data. It means either it masks the data or it creates the noises or it will not allow individual data to take. So this is one of the way that we can protect. And homographic encryption is okay. It's normal. When the secure aggregations, it's like every time when the central server is getting the model data and weights and gradient descents, it secures that at least for 3 days. Or it means security is it makes sure that it is shielded with security. It's when it's shielded with security means it's not that I'm just saying physical and terms data level. We'll we feel it's aggregated in terms of security, then we'll go for training the decentralized one, or else we will not do that. That's what it means. So, and then trust execution environment, creating a trust execution environment, so that makes better. So all that is one of the shielding methods that we do. So as I told you, because you say that the data is protected and the data is being masked and everything. But I'm damn sure we will lose that parameter. So that's what I've written here. When the raw data stays put, parameters, updates, gradients can still leak sensitive information through gradient leakage. That's called gradient leakage. Because the gradient optimizer it will have a set of min and max data or between interval of data. So through that interval of data might risk. Okay. So that could be a problem here. Okay. So the solution is FL pipelines can be created with additional privacy laws with the DP and encryption. And so it means they say that you create DP, also you create encryption so that you will not have any problem. You still you get optimized one here. That's what they mean. So some of the things like what is produced. Okay. So 1 minute, I'll have some thirst. I'll take a water and come. 1 minute. I feel a little tired. I'll take a water. Okay. So I think my screen is shared. Right? Any issues?
Yes, I need to share the screen.
Yeah, sure.
Yes.
So I've kept it exactly on. So one small thing, little more small discussion that I want to see. So if gradient leakage was attacked by the network, probably you lose your pattern of data. So the question is here, sir, any of the data is protected, so we will not have any. Listen to me. Definitely, you lose a data pattern. That is a regression pattern, or that what is the factors of influencing, right?
Excuse me,
You
sir.
know, like when you use the LASA or ridge regressions in
Excuse
ML.
me, sir. Sir, screen is not shared, sir.
Oh, that's what I
Yeah,
was.
yeah.
Okay, okay. I'll do again.
Yes.
Is that fine? Now it is okay.
Yes, sir, it's visible now. Yes,
Oh,
thank you.
sorry.
Thank you, sir. Yes.
So, in fact, that's what I've highlighted here. It might leaking the gradient leakage. Sometimes it leaks the pattern of data. Too. Maybe I don't. I was not telling that before in this conversation. So that pattern is also it's very vulnerable that we lose something. So now the question starts from here. Hey, are we in federal learning also we are losing something on this? So maybe for that only we brought the secure methods and so on. Okay. So that's an ecosystem that we are trying to bring it. Okay. Right. So now I think we have discussed the pipeline methods. In the pipeline methods, we have discussed how we take stages. And the very important thing we have discussed about the privacy methods and what privacy methods I can bring here. One is the masking method, and along with the masking method, differential privacy, creating mathematical noises, and hiding the data pattern, and bringing the encryption formats, and make sure that firewalls also introduced to check whether the data has been done secured or not. All these things. Now, from this, we'll see in a production level, in the pipeline of this production level, uh, in which are the places we have taken already. So, like the Google and Apple they've developed this. So they've developed some of the Siri personalized methods, keyboard predictions, a photo intelligence they already done. And Google, they done a smart reply already. See, when you see in mail, actually, when you pay that, the premium model, now the Google is giving a smart reply. In fact, now like the perplexities and all, you can connect through Google, and perplexity will come and reply for you, and notebook LM. Sorry, we have a note actually through notes also we can integrate. So like this smart reply can be enabled for this federal learning that can be done better. Of course, Android personalization and Gboard optimizations. The Gboard optimization, something we can do it. And the very important when it comes to the healthcare, healthcare. Uh, in healthcare, NVIDIA has created a very important product called NVIDIA Cloud. It enables the hospitals to collaborate in training the medical AI models without moving the patient records. So, in fact, this is one of the top research or top achievements from NVIDIA as a product. In fact, it's very important. Of course, now the question is there, sir, is it we as we achieved in India or in rest of our regions? No. In NVIDIA also, they have not brought it that great commercial, this particular product. They are trying to compile with the regulations of their own US government and GDPR 1. But if they're trying to come up with a little more better of collaborating with the AI models. Now, in fact, it gives a new health movement. This NVIDIA cloud enabling this hospital to collaborate medical AI models in both ways. One is the hospitals can, they don't want to, they can sell their they can sell their practices, the best practices. So they have already, they give treatment and for that they make money. So instead of making money for the treatments, and that's one way, whatever you treat, you can sell the treat by using this model trading, and you can give to the global world. Either you can sell or you can use for free for the service of the interest or maybe service of the society. Sorry, interest of society, and you can make a service. But that's another way that the people have to think. It's not I'm talking about that, but as a business you can see you can create it, and maybe you can also make one time you do a treatment and you can sell that. It means like selling of best practices. Now when you do this for a quite a period of time, then it becomes like everybody can get every personalized treatment methods, and they can choose the best one for the patient, and they can start inducting that to the people. And finance, of course, for this IBM, they have got VBank application. The VBank is federal learning for fraud detection and financial intelligence. As I told you now, the Claude is also added here. Claude, bank automations, bank intelligence, they brought it here. So Claude is also included in this finance sectors. So here what we can do is the transactional data. I know I cannot give the entire transactional data to someone else. So I can take to the federal model, I can give the pattern how it is going. And when, so if this pattern is there, we can give the loan. If this pattern is there, we don't want to give loan. Something kind of very interestingly, we can add and we can show them. Okay. And yeah, so these are some of the examples that I can say. And yeah, if you see here, the Google Gboard, I was taken this because it was used now also. Maybe if you go to Play Store, you can take this. It trains the, when you use the Gboard, maybe end of the session, you can just go to Play Store and you can search for Google Gboard. In Play Store, you'll be getting it. You can install that. Microsoft has got Microsoft Board. Okay, it's a keyboard actually. What is the good thing is, it will get the data from you. The model will come and sit along with this Gboard and Microsoft board. The model will come and sit on your machine. So the model will work closely with your data. It gets trained, but it will supply only weight and parameters to the global Google server, but others it do not serve. So by that, when you chat, you will get the recent activities that you have done, and also based on that, the suggestions will be improved. Okay, so that's what we can say. The good, one of the good example for for FL models that we create here in today's world. Okay, so maybe a lot of examples we can say, but why I've taken this Siri and Gboard and the VBank and NVIDIA NVIDIA Clara, all these models will tell you that simple way that people are making amazing factors, and they are doing great. Okay, now let's go for a discussion what will be the future of this FL, Federation Learning Intelligence, especially when you build like this? The number one already, like, in fact, the Ericsson, the Nokia, or in some of the top telecom companies of AT&T, for the 6G networks, they are going to use this federal learning. It means that they wanted to create this is for low latency process, and they wanted to do for the higher impacts for for the devices, and they want to keep moderated of learning methods happening in the centralized one, decentralizing and centralizing one. Okay. So in that way, 6G and edge computing will enable the ultra low latency collaborating with AI, which we are going to see. Maybe in India it has not been taken place. Probably in some Western countries it's already there in 6G and they are working on that. Probably it will take some time for us to configure it and we can see. And there are other like TinyML and FL models. The extent is very small, and it can be it can be used for sensorical and embedded systems. And of course, in fact, I told you, right, the blockchain. We have started for the same problem. We have started the blockchain. Then we have ended with doing research that we can bring a full AI model there. So in that way, replacing the central aggregations, servers with trustless, dismiss the distributed ledger systems to manage the model. Okay. So we come from the blockchain to decentralized, and from there we can take. So in a future that IoT based devices, IoT based interactions, all that we can bring a little more larger and one. So in future it will be a more decentralized, the more privacy of preserving to the edge level, of course, the more autonomous that we can say, and also the more scalability. Now, we can ask the question ourselves, what is that more scalability and what it implies to us? In fact, it's expected to be like when you say decentralized, the devices will have small devices. As I told you, a Gboard or a Siri, the data will be stayed in here, the model will come and sit along with the application, it will get trained. The model will take only the weights and parameters, it will not. So we call it something like SLM, small language modeling also. It's not LLM, large language model, SLM, small language models. And also you're when you're not leaking the data, you protect the privacy, and so that the networks also have independency, and it's called low latency too. You are not using the just like that. You are not sending it. So for example, again I'm taking the Zomato just for understanding. So everybody is going to the restaurants. It's not only you go to the restaurant, you take a bike, you spend some fuel for that, and you go to the road and you meet the traffic, or you will create a traffic and then you go and do, and you take a food. Doing all these things, you sit and okay, you sit in one place and you order food. One person will take 10 food to the 10 people. So the less traffic, the less productivity in terms of the one who spent money for all these things, and you earn everything once sitting in one place. So the same concept applies here. Instead of sending data across the network for a single model training, you bring the model in a lightweight foot to the devices. The devices will get the data to train, and so that the traffic, which the data, when the data is going from one end to other end, which the data traffic which is creating is prevented. It is not only preventing the data traffic, it is also enhancing the latencies. It means the low latencies, the network bandwidth is effectively utilized. It takes a priority to the data, and accordingly the network is used. So in that case, you are achieving three things. One is the privacy, you sit in your place, and one is you avoid network data traffic. You are not creating, and you are also not in the trouble of created one. Number three is you also what is say, you also bring um, latency level better to your own network. and for the entire ecosystem. Now, when we're talking about all these things, now what is happening is the scalability. It means that instead of bringing data from one devices, okay, you can bring in any devices, probably from a small temperature sensor data, from a mobile, from a TV, from a car. Especially when you see today, autonomous vehicle cars are being getting up, like all BYD or Tesla, or I mean, so many companies are doing a lot of research in autonomous vehicle thing. Of course, already it is done in some Western countries, but coming to India, like traffic, it's very difficult. Now, the lot of research are going how we can do it in India, and so that the market sizability will be better. So we are trying to get the data in different source of devices, not in one or say two. We try to get millions of types of different types of devices. From that, we are trying to push the data. So that's what we talk about the scalability here. So autonomous, privacy, and trying to keep decentralized. It's still centralized for intelligence, decentralized in data, but centralized in intelligence. So that's what we talk about it. All these things, by having this FL pipeline, we can achieve in better way. So by this, what you can do, if you ask me in the research level, you can take research to images, research to hospital level. It's not only for all these things. For some best practices wherever you require, either in manufacturing, either in service industry, supply chain, in any way, I'm just telling you, in any way we can bring this and we can make, wow for this. So I think that's the one thing we can do, and we can make great on this, right? So maybe in a way that the future of federation intelligence, uh, maybe we make better use of this DC blockchain in another way from enhanced one, and we use SML models, small uh, like language modeling in a better way. Of course, the edge computing can play a vital role here. Edge devices, edge computing, and edge networks, and all that plays vital role here. And because of this FL PL models, the network can be a better and highly compactable and utilized one. So all these things you can achieve, and of course you can bring in more way. So it's that's what the FL is not only for privacy, it's for architecture of scalability. It's also for low latency, or for the deep enrooted connectivity of edge computing and edge devices. For all these things, FL can be used. It's not only for. We started talking for the data. Now we ended with talking about the scalability and so on. Yeah. So I guess we have covered everything, and for the given time. So maybe based on whatever you understand, can you answer for these questions? Maybe anyone. So, what is the one of the major, you know, maybe just based on the questions you can answer me. Anyone, can you answer? I think it's available in the screen. Can you answer for the question? Maybe you can put chat GPT also. You can answer. What is the? Sorry, I moved it. Or my screen is available, right?
Yes, sir.
One. And just simple questions based on my the session. I've just drawn here a question. Yeah. So, what is one of the major advantages of federal learning? Centralized storage requirements or increased raw data, improved privacy preservation, removal of local devices. Maybe you can type an answer in here in chat. A, B, C, D. So the answer is C, improved privacy preservation. Okay, what is the main area of federal learning and what it does for us? stores the all data at once, so share raw user data publicly, train model locally without sharing raw data, delete local data of training. No, see, train models locally without sharing raw data. Yeah. Yeah, anyone? Nobody answers. Train models locally without sharing raw data. In federal learning, what is usually shared with central service? So what will share actually? In federal learning, what is usually shared with central service? So we'll share the model updates and grades. C. Again, C is the right answer. Yeah, very good. Thanks. I think someone is there for me to answer. Same, I can. Which problem is reduced by federal learning? So what actually we have achieved by FL and what we have achieved? Privacy risk. What we have achieved? Privacy risk. We are reducing our risk actually. We are making more larger. So privacy risk is the right answer. Yeah. A. What is the role of a central server in federal learning? Maybe I'm just repeating the question. Still. No. Any answers? A. What is the role of a central service for data learning? Stores all the personal data, no shutdown clients, devices, no coordinate and aggregate the updates. It means it's not only getting that for first model, it gets all the models and combined together, it finds an average of that, and that average we call it KL updates. Yeah, sorry, FL updates. FL. Centrally and centralized. Now, any questions are there? Any questions for me? Any questions?
Yeah,
So
dear
almost-
participants.
Yeah.
Dear participants, do you have any questions?
I know how much you got me in the content. Maybe I'll at the end I'm just getting a little tired. Maybe talking for an hour, more than an hour. Yeah.
So, dear participants, if you have any questions or clarifications, please unmute yourself and ask. Sir is here with us to clarify your doubts. Please, anyone having any doubt?
I told you and as I said, we worked in this. So in fact, I got a more experience of working with FL rather than of understanding of this theory. And in fact, I want to show you an experiment in Python, PyTorch, or PyTest. For Flower actually. But in a given time, I guess it's going to be too elaborately because it's a very deeper, the codes and all. It will not. It's easy. It's not easy to get into this 1.5 hours of fitting to understand. So, but anyhow, I've just conveyed you what we have done in real entity, especially for defense by using this AI. In fact, I have used that, so I am very confident on this. And we have given solution. In fact, now the POC proof of concept is used in our. To be very honest, that we can say in our Indian org is using.
Thank you, sir.
Yeah.
Yes, sir. So on behalf of our institution, yes, sir. Yes, tell me, sir. Anything else?
So, and anything is there, you maybe post questions and interactions. We can take it and we can mail it. Thank you for this opportunity.
Yes, sir.
And
I also thank you, sir. So on behalf of our institution and all the participants of this faculty development program, I would like to express my sincere gratitude to sir for delivering such an insightful and engaging session on building a federated learning pipeline. Sir, your vast industry experience and deep expertise in emerging technologies were clearly reflected through today's session. The way you explained the concepts with practical relevance and clarity has provided us with valuable insights into federated learning and its real-world applications, sir. Your dedication to technical training and your remarkable contributions in bridging the gap between this academia and industry are truly inspiring, sir. The knowledge and perspectives you share today will certainly help all of us enhance our understanding of this important domain. And we are truly grateful for your valuable time, effort, and willingness to share your expertise with us, sir. It was an honor to have you with us in this faculty development program. Once again, I thank you, sir, for your excellent session and for making this program highly enriching for all the participants. Thank you so much, sir.
Thank you, ma'am. Thanks for this opportunity too.
Yes, sir.
And thank Purnima ma'am, and Saranand sir, and Akila ma'am.
Yes,
Thanks
sir.
for
Thank
all.
you. Thank you so much, sir.
Thank
Yes,
you,
sir.
sir.
Yes, sir.
Thank you, sir.
Thank you. Thank you, sir. Yeah. Fine. Bye.
Yes,
Have a good day.
yes, sir. Thank you, sir. And I request all participants to rejoin the meeting at 1:25 p.m. because our next session will sharply start at 1:30 p.m. And also we have posted, we have the feedback form link and chat box. So I request all the participants to kindly submit that feedback form because you need to maintain at least 80% of attendance in order to receive your certificate. So I kindly request everyone to kindly upload your feedback form. Thank you so much. Yes. Very good afternoon to everyone. Welcome back to the post-lunch session for our FDP. I hope the break has refreshed you all. Thank you for rejoining on time. We are happy to proceed with the next session, and I encourage everyone to stay connected and gain maximum benefit from the expert insights being shared by today. It is my great pleasure to introduce our esteemed resource person for this session, Dr. A. Sivaranjani. Dr. Sivaranjani is an accomplished educator and currently serves as an assistant professor in the Department of Analytics, School of Computer Science and Engineering at VET Vellore. With over 12 years of teaching experience, she has developed strong expertise in delivering courses across core computer science domains with a balanced focus on both theoretical foundations and practical applications. Her research interests span several cutting-edge areas, including artificial intelligence, machine learning, deep learning, computer vision, and Internet of Things. She has made significant contributions to the research community with more than 25 publications in reputed journals and conferences, reflecting her commitment to the advancing knowledge in emerging technologies. Beyond her teaching and research contributions, Dr. Sivaranjani has actively contributed to academia as a jury member, session chair, and resource person for numerous workshops, conferences, and faculty development programs. She has also delivered expert lectures on highly relevant topics such as generative AI, agentic AI, and machine learning. She is deeply committed to the mentoring students, guiding innovative research projects, and fostering academic excellence through excel through knowledge sharing and professional development. Today, she will be delivering a session on federated learning system design, a highly significant topic that explores the design and implementation of decentralized machine learning systems. We are truly honored to have her with us today. Please join me in extending a warm welcome to Dr. A. Sivaranjani for this insightful session. Ma'am, we are delighted to have you with us and look forward to your valuable insights. Now, I request Dr. A. Sivaranjani to kindly take over the session. Please, ma'am. Okay, ma'am. Are you available there? Yes, yes, yes. Excuse me, ma'am. Please unmute yourself, ma'am. Yeah. Thank you so much, ma'am.
Ipo, am I audible?
Yes, yes, ma'am. You're audible now. Yes, ma'am.
Okay.
But your screen is not shared now.
Yes, now I will share.
Yeah, ma'am.
Now my screen is visible. Please, someone answer.
Yes, ma'am. Yes, ma'am.
Okay, thank you.
Yes.
Sorry for the delay. Actually, I got stuck with some settings problem. So sorry for the delay. Sorry for the inconvenience.
No
And
problem.
I would like to thank for the warm welcome. And I would
Thank
like
you so much, ma'am. Yes, ma'am.
thank for this opportunity. And I would like to thank Dr. Purnima ma'am also.
Yes.
Without delay, we will start the session now.
Yes.
So today
Yes.
we are in the third day of your FDP, and today's session is Federated Learning System Design, right? So let me start with a quick check, what are all the terminologies you have heard from your last three sessions? I'm asking about last three sessions, not entire FDP. Only last three sessions. So I want to see the response in the chat, quick response in the chat. So what are all the terminologies you heard from the last three sessions alone? I am not talking about past 3 days, from yesterday afternoon session and today morning 2 sessions. So
So
what?
yesterday afternoon we have classical federated learning to quantum paradigms like core concepts and limitations, ma'am.
Yes,
Yeah,
ma'am.
and
Yes.
today, early session, we had advanced federated aggregations algorithms.
No. I am not asking the topics, but I am just asking general question to the audience, like what all the terminologies they heard from the session, what they observed, what all the concepts they heard, what all the concepts they learned. So just I want to know how was the session and what all the things they learned from the session. So just give it in the chat, audience. Faculties, quick response in the chat. Some terminologies, any terminologies, like you may heard federative learning, aggregated algorithms, strategies. So like this, what are all the terminologies you heard from the last 2 sessions or 3 sessions? What are the terminologies you heard? Just participants, 44 participants are there. Yes, federative learning from Sabri Rajan sir. Apart from federative learning, what else? Since this is an afternoon session, you people might be feel sleepy. Yes, quantum computing. Response from Dr. Hemalata ma'am. So I'm expecting the session should be somewhat interactive. So then and there I will post some questions. So try to give response for the questions so that it will be interactive. You won't feel sleepy also. As variance reductions from Nandini. Yes, any other answers? Okay, no issues. So we had some terminologies. Before getting into federative learning, I want to tell how this federative learning evolved. So from the IID and non-IID data in federative learning, very good, Manoj Sagar. Okay, so we need to know how the federative learning actually got evolved from the classical centralized machine learning. So in the earliest machine learning days, when machine learning was introduced, those days, actually, so what we used to do is different clients will be there and the data will be collected from each different client and it will be stored in the server, and the global model will be there and that model will train all the data. So here the thing is we need to bring all the data to one location to train your model. Okay, so that is the concept of earlier centralized machine learning technique, that is classical centralized machine learning concept. But how this federative learning arised from this? So in the centralized machine learning concept, there are many issues actually. There are a lot of issues we faced. The issues like privacy concern, the issues like distributed computing, and due to rapid growth of edge devices like smartphones, IoT. So because of these issues, federative learning actually arose. So these is the reason. These are the main reason for like evolving federative learning evolvement actually. So the core problem. Still, if you want to understand the core problem, let us consider this. This one example: disease prediction system using data from different hospitals. So in the traditional centralized machine learning technique, if you are going to use that, we need to collect the data from all the clients. So here, whatever the pictures I have given, like hospitals or buildings, it is actually client. And apart from that, we will also collect the informations from the ambulance, in the ICU beds. Yes, like this, we used to collect a lot of records, like lot of patients' records through these kind of sensors or through this kind of nodes. So here we are going to consider everything as a node. So all the data will be collected from these nodes and it will be collected in the server, some centralized server. So in the centralized server, what the first thing will be pre-processing, after that feature extractions. Then we used to train the model with some global model. After that, we will dispatch the model to individuals. Okay, so that is the concept behind this earliest classical centralized machine learning technique. But the issues like privacy risk. So if you take banks or a health domain or bank or financial sectors, so we need to, if you want to transfer the data from one place to server or centralized node means, so the trust issue will be there. So that privacy concern will be there definitely, right? So to like that, we are also having some other issues like massive bandwidth. So because of this growth of massive bandwidth, the large amount of data actually evolved, and so transferring this data to the centralized one is a difficult one, and training all this like we need to develop a model to train all the data, right? So these are the issues we faced in the classical centralized machine learning model. So if you want to transfer data from one end to another end, so from one local end to a global end, we need a bandwidth. So if the obviously if the data growth is raised, obviously we need the bandwidth. Obviously the cost also will get increased. And one more disadvantage in the centralized model is, if one point failure, if there is a one failure in the centralized server, every local device will get stuck. So the complete system will get failure. So these are the issues actually, these are the issues which is act as a reason for federative learning. Now, so then if we don't want to transfer the data from local to server, local device to central server, then what is the way? Then how we are going to train the model without transferring data from local node to centralized server? How we are going to train the model? So what is the way? How we are going to do this? So can I get a quick response for this? Can we train a model without transferring raw patient data? So from in the previous slide, if you see, the main core idea is you want to transfer all the data from the local device to centralized server, right? But there is a issue behind this. Then how we are going to do this? Any idea? Because last two sessions you people were in the federative learning only. Federative learning session. So you can answer for this question. Can we train a global model without transferring raw patient data? So without transferring data, how we are going to train the model? So instead of transferring the data, we need to transfer the model. That is the answer for this. So that is how this federative learning actually, the transition from the classical machine learning to federative learning actually happened. So instead of transferring the data to the centralized server, what we are going to do is we are going to build a global model and we are going to transfer the model to the clients instead of transferring the data, so that our data will be secured. So the privacy concern will be that there will not be the privacy threat will not be there. So here we can handle this kind of collaborative learning. So this kind of collaborative learning is called federative learning. So the thing is, from the centralized server, we are going to do is we are going to transfer the model instead of data. So that is the point you have to remember. So that is the difference between centralized machine learning and federative learning. So the thing is here, n number of nodes will be there, n number of clients will be there, and each client will hold different data. And to train the data, to train those data, what we are going to do is we are going to build a global model. It will be stored in some server or some cloud, and that model will be transferred to each device or each local devices. Okay, so that is called federative learning. So these are the core ideas behind this federative learning. So instead of having transferring the data, we are going to transfer the global model. So the federative learning is nothing but it is we are going to train the statistical model, okay, but in the remote end, not in the server side. Okay, that is the federative learning. Now see this architecture diagram. So in the federative learning, the four main core components are there. So four components are server, client, global model, and local data. So without these four components, you can't deal with the federative learning. So the four main components are, so the global model will be there, and all the client will have the local data, and server will be, the global model will be deployed in the server. So initial weights will be there, and all the local client is going to download the global model, and it is going to train the model with its own data. So each local device is going to, each local device, or it might be each local host or a node, whatever. Okay, it is going to train the model in its own local host. Okay, not in the server. So after that, what it will do, so what is the pipeline behind this federative learning is, so initially we are going to initialize the global model, and that global model will be transferred to the local device. So the global model will be trained with the local data. So suppose we are having 4 different clients, and the global model, the same global model will be trained by all different 4 local data. Okay, so the local data which is stored in the client. And once the training is over, what it will do is it will send the updates to the global model. So all the client will send the updates. So whatever the updates it got from after the training, each training, so it will send the updates to the global model. So that is the pipeline behind this federative learning. So next is, okay, so now I am talking about, ma'am, ma'am. Full screen mode varலையா? Okay. So in the previous slide, I was discussing about this 4 different clients with the local data, and the global model will be there, and this global model will be downloaded by or transferred to all the local client, and this local client will train the model with the local data what it is having, and after the training, it will send the updates to the global model. So this is how this federative learning pipeline or the workflow of the federative learning will happen actually. Okay, now the client sends updates, I said. So once in each client, the training is over, means once the model is learned all the data and it is ready to give the like solve the problem, like either classification problem or any prediction problem. But it needs to send the updates, I said. What is the update? What it will send? Any response? So in the previous slide, I said that after each learning, the client will send the update, I said. All n number of client, or how many number of clients you have. So in this diagram, we are having 4 client, and all the 4 client is going to send the updates, I said. What is that update? So it will send the updates to the global model. What is that update? Any answers? So what is that update? Any answers? Participants, please answer. So what it will update? See, you know the difference in the centralized machine learning, we are going to transfer the data to the server, central server. In the federative learning, we are going to transfer the
Model, ma'am.
model to the local
Global, yeah.
client. Okay.
Yes, ma'am.
So once the model is trained in the local data, local client, again it has to give the updates. What it will update? Updates means what? So here, okay. So the updates means nothing but it is a numerical value, that is gradient. So each local host will have the gradient value, and those gradient value will be updated in the global model actually. So the gradient is actually in which direction or how we are going to change the model to reduce the error. So that is called actually gradient. So whoever learns machine learning, you all heard about the term gradient, right? So the gradient is nothing but how you are going to reduce the error actually. So the gradient function is nothing but you are going to how you need to reduce the error actually. So that is called a gradient. So here, if your model wants to perform efficiently, means you want to reduce the error. So error means loss here, loss. Okay. So with respect to weights, we need to reduce the gradient, or we need to reduce the weight of your model. So that is called the update. So every node should sends the updates to the global server. Okay. So it is not going to send the model. It is going to send the updates alone. Are you getting? Okay. Next. So after updating, what will happen? So now in the federative learning, so global model is ready. So all the data are in the local client. So all the local devices is going to download the global model. It is going to train the model in the local node itself or in the client itself. Once the learning is done, it is going to send back the updates alone. Okay. So once the update is done, so what it has to do? So it is going to collect the updates from different clients, right? So see here. So this is the global model, and here, so this is your global model, and here all the device client is going to download each model. Okay, so the same model will be downloaded by the each client. So once the learning happens, so all the data will be stored in the local device only. So all the data are here only. So we are not transferring the data here, only we are downloading the model here. So once the learning is done, it is updating. So updating, what it is updating? It is updating the weight, or it is updating the gradient, or it is updating the status of the model. Okay, it is updating that. So what it will do is, here in the centralized server, what it will do is, it will aggregate all the weights which is collected from the different clients. Okay, so based on this, it will again redefine the model here. So what it will do is, from the system 1, the error is somewhat okay. From the system, from the client 2, the error is very, it is drift too far. And from the client 3, it is somewhat moderate. So accordingly, it needs to concentrate all the clients, right? So it can't be biased to one particular client. So it needs to, what it is going to do, it is going to do the aggregation. So after aggregating, it will modify this model, and again it will send back the model to all the clients. Again all the client will do the same procedure. This client 1 again will download this model, and client 2 again this download this updated model, and client 3 again update the download the same model again. Second iteration or second round. Again it will continue, again it will update. Like this, it will go for some rounds. So how many rounds we need to define? Okay. So that is, so this is this is the entire workflow of the federative learning. Now, for this aggregation, we are having certain techniques. So many strategies are there. Aggregation algorithms are there. Different approaches are there. So this also you have studied in your last session. So these are the core aggregation algorithms. So these are the very commonly used aggregation algorithms. There are many aggregation algorithms are there, but we are going to discuss only these 3 aggregation algorithms today. So the first aggregation algorithm is Fed average, Fed prox, secure aggregation. So Fed average is nothing but it is going to collect all the weights from the client 1, client 2, client up to n. So all the weights will be collected, it is going to take the average here. So that is the Fed average. Okay. So here, this nk by n means how many number of samples in each client. So it is going to take the average of those samples. Okay. Then Fed prox. So Fed prox, it is actually the first one is very simple, very effective, very commonly used in all the federative learning algorithms actually, compared to other algorithms. This Fed prox is, so whenever we need we are going to handle the heterogeneous data or heterogeneous system, that time we are going to use this Fed prox. So the Fed prox is nothing but we are going to introduce the proximal term. So the proximal term here is this W, this one, W minus W power T. So the, sorry, not that one, this one. This mu is the proximal proxy term actually. So this mu here, this is the proximal term. We are going to introduce this proximal term in the local function, the objective function, where we are going to use in the client. In n number of clients, we are going to use the objective function, right? There we are going to use this mu actually. So when we are going to use this Fed proxies, heterogeneous data and heterogeneous systems. So the heterogeneous data means, let us consider client 1 is dealing with, let us consider the healthcare, some hospitals. The hospital which is present in Chennai is having some kind of data, malaria, dengue. And the hospital which is present in Ladakh, they are going to deal with some other kind of problems. And the hospital which is present in Gujarat, they used to deal with some other kind of problems, right? Health issues. So each zone will have different health issues. But we are going to frame the common model, global model. The global model is going to deal all the diseases, right? So here the model should not biased with one particular client. So here we are introducing this prox term. So whenever we are having this heterogeneous type of data or heterogeneous type of system, that time we are going to use this for Fed prox. Next is secure aggregation. So secure aggregation is now, whenever in the federative learning, as I said, we are going to send only the updates, not the data, or we are going to transfer the model instead of data. And once the training is done, we are going to send the gradient, right? So using that gradient, we may think it is our data is very safe and there is no privacy threat, but still we can reconstruct the original informations from the gradient also. So using the gradient function also, we can reconstruct the original information. That is called a gradient inversion, we used to say. So gradient inversion or reconstruction, we used to say. Okay, so to solve that problem, we are introducing this secure aggregation. So here what we are going to do is, instead of sending the updates directly, we are going to use some masking technique. Masking technique means even the server itself, it is not going to see the original update from the client. So what it is going to do is, instead of showing the original update, it is going to add some mask value. So masking value means some random value. So here this RK is the random value. So using this random value, what we are trying to do is we are trying to hide the original weight which is shared by the client. So even the server itself can't see the actual weight from the client. So that is called a secure aggregation. So these are the core algorithms. So this core algorithms, what is the role of this core algorithm? So here actually it is going to act as the fundamental foundational mechanism. So in the federative learning, without this core aggregation algorithm, we can't proceed, right? So because it needs to collect all the updates from the client. So it has to consider the privacy, it needs to consider the performance. So and it also needs to consider the different data distribution and heterogeneous type of devices and communication efficiency, because every time the client needs to update the weights, right? It needs to update the weight to the server. Okay, so there should not be any communication issue also. So so this core aggregation algorithm is the important fundamental concept in the federative learning. So it needs to deal all these four important factors, what I said. So next is, this is the workflow of federative learning pipeline. So initially, we are going to initialize the global model, and next we are going to select the client. So here it is actually another approach. So here what we can do is we can include all the client, we can like all the client can participate in the learning. Otherwise we can select. So this is different approach. And next is model distribution. So all the client will download all the models. The next is so it will be trained. So in the local client, the model will be trained using the local data. So here this SGD is the stochastic gradient descent. So it will using this stochastic gradient descent. It is optimization technique actually. So using this stochastic gradient descent, it will update the weights. So after the updates, after the update is computed, will be updated to the main server. Okay, it will compare both the things. So again, the server will aggregate all the weights from the client. So if it is okay, if it is converged, we used to tell, what I said is the error should be reduced, I said. So the error should be in which direction, or how we are going to reduce the, how we are going to change the model to reduce the error, I said, right? So that is called the gradient. So here how we can say is that term is called convergence, how it is actually converged. Whether if it is converged like minimum, if it is converged to maximum, means based on that, if it is maximum means it will again go to next iteration, next round again. Otherwise it will finalize the global model. Okay, so this is how this federative learning will work actually. Next, these are the different real world applications. One interesting application I will tell you, in your Google, in your smartphone, if you are using Google keyboard, right? So that Google keyboard, what it is doing, the Google Indie keyboard and all, it is translating, and based on your texting format, texting pattern, it will save all the words in your Google Gboard, right? Google Gboard, that is called Google Gboard. So it will like if you are texting in Tamil, if you are texting in Tanglish, it will save all the words, right? If you are using some word alone, like your partner name or your friend's name, that particular name will be there. It will be stored in your thing, right? How it is actually happening? So every time the whatever the text you are sending, it is not actually stored in the server. You are sending message to your friend or your partner, that is not actually stored in the Google server. So what it will do is, in your phone, in your smartphone, the model will be there. So that the model which is actually deployed in the Google server, it will be downloaded by, or it will be used by your smartphone. It will train locally in your phone actually. It will not train in the Google server actually. And likewise in your Google Photos, right? So the Google Photos, actually the photos stored in the Google Cloud, but there is a model in your phone. So using your phone, it is accessing the cloud, but still the federative learning concept is like the model which is deployed in your phone is actually training your data set which is stored in your phone. Okay, so that is called a federative learning. So likewise, this autonomous vehicle, if you see this autonomous vehicle and the smart devices and all, so many sensors will be there. Every time then and there it will try to collect so many informations, and those informations will be stored. Those informations will need to be stored locally. So you think about that, if every time the whatever the informations which is collected by, so in the autonomous vehicle, so many sensors will be there, or LiDAR, like LiDAR, temperature sensor, humidity sensor, like this, so many sensors will be there. So every time if the if you are having n number of autonomous vehicle, every time all the vehicles are sending informations to the cloud, and again the model is going to train the informations in the cloud. Again it needs to send the decision to the autonomous vehicle or to the client. That is difficult, right? So instead of that, what it is going to do is, in each autonomous vehicle there will be a small model will be there, that is actually controlled by the several centralized server. So whatever the if the model trained the local data, what it is collected in each autonomous vehicle, it will send the updates alone. It will send the core update to the centralized server, not the complete data or not the complete model to the server. Okay. So these are the applications, real world applications of federated learning. And next, so this is a quick question. Just respond for this question. In the federative average algorithm, so this federative average is the algorithm. We have seen 3 different core algorithm, right? Which exactly travels from client to server? Raw training data, or the model itself, or the updates? Which will transfer from client to server? Response. I need response. Someone answer. All madams, all sirs, kindly respond. So in the federative average algorithm, yes, see updates. What exactly travels from the client to the server? Exactly, it is going to send the updates alone. So update means it is a gradient, nothing but it is a gradient or weights of your model with respect to the weights of your model. So that is what it is going to send. So thank you, Akila, Arun, and thank you, Sweetie Julia.
Yes.
Next. Again, another question. So in the pipeline, what happened when you had to wait for all the clients to finish their local training before server could aggregate? What if one client was very slow? See, you are having 5 different clients and all the 4 clients sent the updates. Only one didn't respond. So what it will do? Server side, from the server side, what it will do? Whether it will start aggregating all the weights which is collected from the remaining 4, or it will wait for the thing, or what any other action it will do? Any guesses? We didn't discuss it, but still, any guesses? See, listen, it will wait. Very good. So it will wait actually. It will not aggregate the updates. It will wait for all the clients until if it is a synchronous federative learning. See, there are 2 different types of federative learning. One is synchronous. If the architecture is going to follow synchronous federative learning, it is going to wait. If the architecture is going to follow asynchronous federative learning, it will not wait. So difference between synchronous and asynchronous is like whatever the clients you present in your architecture, all the clients should respond. All the clients should give the updates, and the server needs to collect the update from all the clients. So that is called a synchronous. It can't ignore any one client also. Okay, so that is called a synchronous. Asynchronous means, so it will not wait for the client if it is asynchronous. So whatever the updates it received from the clients, so based on the approaches or based on the strategy, let us consider it is having some 100 clients. So we are going to program the model. If it is asynchronous federative learning, if it received 50, if it is received updates from 50, it can proceed. Like that, if I am programming means it will proceed. So that is called asynchronous federative learning. But both are having some disadvantage. One is called straggler and another one is called stale. So the straggler is nothing but it is waiting. So let us say it is having a 5 client and 4 clients sent the updates and 1 didn't send the update. So the server needs to wait for so long, right? We don't know the reason. It might be a power cut. It might be a computation power, like a slow computation power. It might be some communication error. So like this, different reasons will be there for like the client, like the server didn't get the response from the one particular client. But that problem is called a straggler. And the stale in the asynchronous federative learning, the asynchronous federative learning, it will not wait for the client, but there is a issue called stale. The stale means let us consider we are having 5 clients and from the 3 clients it got the updates. The server got the update, and from the 4th and 5th client it didn't get the update. But based on the first 3 clients, the server updates its global model, and after some delay it is getting a response from the 4 and 5, but the global model already got updated. So now only the 4th and 5th is sending its update. Now the global model will be outdated, right? Because it didn't consider the 4th updates from the 4th and 5th. So even though the global model is updated with the first 3 client, it is still outdated because it didn't consider the 4th and 5th. So that problem is called a stale. So this is actually because of waiting, and this is actually because of outdate. The stale is because of outdate. This is because of waiting. Okay. So next. Okay, so these are other problems. I don't want a response, but still try to understand the problems. What are all the problems? So the first problem is like, suppose, so far we are discussing about 5 clients, 10 clients, right? So just imagine, I didn't go for 100 client also. So just imagine if the client is from 100 to 1,000, 10,000 clients. If you are having if you are designing a model and suddenly the client got increased, you designed a model only it will handle up to 100. Initially it was 100, and suddenly or day by day it is getting increased, and at last you got, like in your client side you are having some 10,000 client. Then how you are going to deal that? So this is actually one challenge, and we used to call this challenge as a scalability. Okay, and next thing is scalability. Scalability is an important issue in all the distributed systems, in all the machine learning or deep learning, wherever. Without dealing the scalability problem, we can't solve any, we can't design, or we can't invent any algorithms. Okay, so whatever the algorithm you are going to design, like you are going to develop, it should handle the scalability problem. And next is the we are having 50 hospitals. Okay, in the 50 hospitals, suddenly 23 hospital gone offline. So gone offline. We don't know the reason, whether it is a power cut or network failure, or we don't know anything. It just gone offline. So what is the how we are going to solve this problem, or what kind of challenge it is? So here also the server needs to wait. So here, if it is a synchronous federative learning, it needs to wait actually. So how you can solve is, you can go for asynchronous federative learning, right? And the next problem is this example we already discussed in the previous core algorithm concept, right? So we are having n number of clients. So one client is from Chennai, one client is from Ladakh, and one client is from Gujarat, and another client is from Kerala, another client is from Rajasthan. Like this, we are having n number of clients from various zones, right? So each zone will have different types of diseases. The people who are living in those areas, they will suffer from different diseases. The reason might be different, the cause might be different, the diagnosis might be different. So everything is different, right? So here we are going to deal the heterogeneous data. So whatever the global model you are going to develop, it should not be biased for all the client, which is whatever the client you are going to transfer this model, right? So it should not be biased. So so to solve this problem, what we can do is we can use this Fed prox. So this also we have seen, right, in the core algorithm core algorithm concept. So Fed prox. So you have to introduce the proxy term, that mu. Okay. So by introducing this, we can eradicate this challenge. So we know the workline, we know the workflow of the federative learning, we know the core strategies, so aggregation strategies, but still we are having so many challenges. I have mentioned only 3-4 challenges here. So if you are going to develop a real time, you are going to develop a federative learning system in the real time. Okay. So what are all the challenges you will face? Okay. So design challenges, and how it will be, how you are going to design the system, how you are going to develop those system, and how you are going to solve those problems. Okay, so that is called a design system. So that is actually federated learning design system. So this system is like how you are going to build the federated learning system by handling all the challenges, and it is like it is going to give the complete structured organized, like it is going to give the like you have to deal the coordination mechanism, like you have to get the updates from all the clients, and the synchronization strategies, whether you are going to wait for some client or you are going to select only particular client, you are not going to consider all the clients, and different architectures. So what are all the different architectures we have? What different architectures you are going to consider based on the applications, and communication protocols, GRPC or REST. Like we are having a number of communication protocols. Here, communication protocol is a very important thing. Why? Because you need to send the updates then and there, right? You need to get the global model, and also even after training, you need to send the updates. So multiple rounds you have to send the updates, right? So here communication protocol is also very, very important actually. Then coordination, then synchronization strategies, and privacy policy. So privacy policy in the sense, what are all the data, what are all the updates you are going to transfer? With those updates, we should not from the updates, the server, or there should not be any chance to retrieve the original data, because there are many chances. So what we think is we are sending only the updates. With the gradient, what they are going to do, how the hackers are going to retrieve the original data. But still, using the gradient values, we can retrieve the original data. We can predict the original data, and we can predict a certain patient's record also, certain patient's values. We can guess the certain patient's values. Based on that, we can predict the original data. So that is called, we already discussed, gradient inversion, I said, right? Or reconstruction. And what are all the operation rules we are going to follow? So why we are doing all these things? While designing this, or while building this federative learning, we are considering all these things: architecture, communication protocols, coordination, synchronization. Why we are considering all these factors means, because we have to build a reliable securable federated learning system. So whatever the system you are going to build, it should be 100% efficiently. It should work, and the performance should be very efficient, and it should be scalable if you are going to increase your systems, and it should be very reliable and secured one. So for these reasons only, we are considering all these factors. So these factors is going to play the important role in designing the federated learning system. Okay, so in the federated learning system design, the first thing we have to consider is core architecture. So what type of architecture you are going to consider? You are going to consider in your design system. So you have to decide that. So the core architecture, in the sense, we are actually classifying this core architecture into two things. One is cross device and cross silo. So the cross device is so in your architecture, in your complete network, you will have the smartphone devices, sensors, IoT devices like that. That is actually resource constrained devices. So n number of massive amount of resource constrained devices will be there. So those devices will generate n massive amount of data every minute, every second. Actually, it will generate, it will sense the massive amount of data. So that is why we are calling it as a resource constrained device. And here the advantage of this core devices, like it is not necessary to all the devices should participate in the learning. So whenever it is active, it can participate. Whenever it is non-active, like inactive, it can leave the group, or it can leave the cluster. Okay, and here all whatever the data it is going to generate is everything is heterogeneous data. Okay, and this cross silo is actually it is actually a group of organization, a powerful reliable organization with a large amount of data, but reliable data. So whatever the data it is going to have, it will be a reliable one. So for example, hospital, bank, some educational institute. So these are the example for this cross silo architecture. So we have to decide which will be suitable. So in this cross device, the participation of the node will be, the client will be dynamic actually. But in the cross silo, the participation is stable. There will be a static infrastructure. Here, whatever the approaches you are going to follow, it will be static actually. You can't change the participation of the client in between then and there every time and all. But in the cross device, like it is actually a dynamic one. Based on the activeness of the each node, it can participate anytime, whenever it wants to participate, whenever it wants to leave the network. It can decide that. It is not going to affect the entire system actually. Okay, and the next thing is one more two important factors we need to know is, one is horizontal data sharing. So this one, horizontal data sharing, and another one is vertical data sharing. So horizontal data sharing actually, this cross device, every time it will support horizontal data sharing, and this cross silo, every time it will support vertical data sharing. Cross device is nothing but smartphones, IoT devices, sensors like that. Cross silo is what, hospitals, banks like that. Okay, so what is the difference between horizontal data sharing and vertical data sharing? So in the horizontal data sharing, every time the same feature space will be there, but different samples. Different sample means same features you are going to collect, but for different customers. Like that you can consider. Different customers, but same features. Let us consider age, BP, sugar is there or not, like that. Different customers, but same features. So that is called a horizontal data sharing. And vertical data sharing, different features, but same sample, same customer. Let us consider customer A, his health related informations, and same customer, his financial related informations, same customer, his educational related information, so like a resume. but in the resume you don't have health related informations and all, but still you have personal informations and your career related informations, your educational informations, right? So same person but different features you can find in the resume, right? Like that. So that is called vertical data sharing. So in the cross device, predominantly it will support the horizontal data sharing, and the cross silo will support the vertical data sharing. And here it is going to have the same features and different customers, and different features and same customers. Okay. Okay, so this is the core architecture, and also you have to decide the topology. So different topologies are available. So what topology we are going to follow? So suppose if you are going to build a federative learning system, and what are all the based on the application and based on the clients, n number of clients, and based on the requirement and based on the need, we need to decide which architecture or which topology suits more actually. Okay, where we are having three different types of predominantly we are having three different architectures or topologies. So the one is centralized one, decentralized one, and hierarchical one. Okay, so the centralized one, obviously the centralized server will be there and n number of clients will be there. So all the clients will send the updates. So the local model will be transferred to the local clients, and all the local clients will train the model in the using the local data which is having. So after that it will send the updates to the local this server, from the local client to server, and the server will have the aggregate functions and it will aggregate all the updates from the client. Okay, so here this is very simple and fast, efficient, but the limitation is if one single point get failure, the total thing will be blocked. If because the server needs to wait for all the clients, right? It can't proceed without getting the updates from even from a single client. So it has to wait for the complete system. So whatever the nodes or client it is going to participate in the system, it needs to wait for the all the clients. So if any power cut, or due to some bandwidth issue, or due to some communication issue, or due to some computation delay or latency delay, because of this, if it is going to there will be a problem in sending the updates to the server, means then again it needs to wait for the entire time. So that is called as straggling. We have seen in the previous slides, right? So that problem is called a straggler problem. So if it is a synchronous federative learning, then it is a problem only. Then next thing is hierarchical federative learning. So here we will be having a layers. So that's what it depends upon the application and depends upon the requirements. We can construct our architecture based on the necessity, right? So here, if you see, we are having n number of clients. So and here we are categorized this clients into groups. We have grouped into some clusters based on the needs and requirements. So might be this whatever the clients clustered in cluster 1 might be of different data. It is going to generate some different data. It is going to generate some different data, and here also it is going to generate some different data. So to avoid the data heterogeneity problem, like we can go for this also. So what we are going to do is the edge server is actually going to sit on the top of the client. So every time whatever the global model which is transferred from the server, it will be transferred to these clusters, and the model will get trained, and the update will be sent to this edge server, not to the cloud. So instead of this cloud, the updates will be sent to this edge server, so that the edge server will update the global model. So it will aggregate all the informations from the clusters, and finally it will send the updates here. So that is called a hierarchical federative learning. So here the thing is, it will reduce the communication latency problem, that is the bandwidth problem. So everyone don't want to directly communicate the server, right? Instead of directly communicating the server, it will send all the things to this edge server, and this edge server will send the informations to the cloud. Okay, so that we can avoid this communication bottleneck problem. And the important limitation here is coordinating all the layers. That is very, very important. So see, here it is going to deal with the 3 layers, right? The server needs to wait until it got the response from all the 3 different layers and all the responses, right? So again, the coordinating issue is the main disadvantage here. Next architecture is decentralized federated learning. So this decentralized federated learning is no server concept. Everyone will communicate with all the nodes or all the clients. So everyone will be here acted as the client, and everyone will be acted as the server. Like here, that is why we are calling it as a peer-to-peer. No client, no server, nothing. Okay. So the thing is, all the updates will be shared to all the nodes. So all the updates will be transferred to all the nodes which is participated in the architecture. And here again, the problem here is if one node gets failure, the complete system will get collapsed. So that is the major issue here. So these are the 3 different architectures. So that is centralized architecture, decentralized, and hierarchical architecture. And before that, we have seen this 2 different factors. One is which type of device we are going to use, whether it is a cross device or cross silo. So based on this, like we have to decide based on which architecture you are going to use. If it is a cross device, means you are going for centralized or decentralized or hierarchical. So that you have to decide whenever you are going to design this federated learning system. Okay, and the next thing is, next core component is client side component. So in the client side, you have to concentrate a few points. So the one is, see, the ultimate role of the client is it will receive the global model. It will store the data in the local client itself, local storage itself, and it will train the model. So once it computes the local gradient, it will send the updates to the server. So that is the ultimate role of the client component. So here, while sending the updates, it will send the updates in the communication through the transport layer only, right? So we are having, 7 layers, right? So through the transport layer only, it will send the updates. So there will be formats for sending this updates. So that format is very, very important. So we need to know that format. So parameter formatting. So how it is going to send the parameters, in which format it is going to send the parameters. Okay, that is very, very important. And while sending this update, it needs to provide the security. So here it has to follow some security mechanism. As I said, using that update also, like we can retrieve the original information. So to avoid those things only, we are going for the secure aggregation concept, masking concept, and all. Okay, so that is the client side component. And next is server side components. So in the server side components, the ultimate thing is it will initialize the first thing is it will initialize the global model, and it will transfer the global model to the client. Okay, and the client will compute once the computation is done, it will send the updates to the server. Okay, so once it receives the updates, it needs to aggregate all the updates. So that is the primary role of server side. Okay, so while aggregating this thing, it has to concentrate some important factors, like one is security, and also it needs to consider the it has to consider the versioning. So at what round it is actually performing, and how many rounds it needs to perform, and it has to consider the straggler problem. It also needs to consider the stall problem. So if it is using the synchronous federative learning, if it is using the asynchronous federative learning, so based on that it has to handle all these challenges. So this is the core role of server side component. And next is network and communication component. So here this network and communication is also playing an important role here, because the first thing is it needs to transfer the model, and so that the communication protocol should be a reliable one. So while exchanging this model parameters, so once the model training is done in the client side, it needs to update the parameters, gradient. So here the network should be reliable one. If the network is not reliable one or not trustable one, and if the bandwidth is low, then the bottleneck problem will be there. So because then and there the client needs to send the updates. So usually what protocol we are going to use, that is actually matter. So usually for this kind of problems, federative learning systems and all, we used to use gRPC, that is Google Remote Procedure Call. So that remote procedure call will plays an important role here. That is commonly used protocol. And another protocol is called REST protocol. So we have to decide which protocol we are going to use, based on the bandwidth. We have to decide that. And to ensure the reliable exchange of parameters, we can go for this compression and quantization. That is, instead of sending the raw updates or instead of sending the raw gradient, we can compress the gradient, and also we can quantize the gradient and we can send. So that is the core role of this networks and communication component. And this is another important factor, frameworks. For machine learning and deep learning algorithms, if you want to deploy a system, we are having n number of frameworks like PyTorch, TensorFlow, Keras, like that. We are having n number of frameworks, right? For federated learning system design, we are also having some frameworks. So the important frameworks are like TensorFlow Federated, TFF. We used to call it as TFF. So this is actually generated by the Google. It is termed as TensorFlow Federated, TFF. Okay. So the ultimate advantage or the ultimate factors includes in this framework is it will integrated with the TensorFlow, traditional TensorFlow what we are using actually. So whatever the libraries you are using in the TensorFlow, Keras, and we can integrate with that. And it also provide two APIs. One is Federated Learning API, another one is Federated Core API. So this Federated Learning API is TFF.learning, and another API is TFF.program and TFF.computations. So here, when we are using this TFF.training is when the client is actually training the model with the local data, that time we are using this TFF.learning. And whenever we are trying to compute the gradient, so the computations, and when we are transmitting the updates from the client to server, and when it is aggregating it, then we are using that TFF program. So what aggregating strategy you are using, what aggregation technique you are using, so that will be decided by this TFF program. And this TFF computation is a gradient computation for computing gradients. Okay, so these are the two API actually. It is provided by this TFF. So I will show you code here. So you can, in this code, you can see, so this is TFF learning.algorithm. So here it will decide what algorithm you are going to use, what optimizer you are going to use. So this is completely for what algorithm you are using. Okay, that is server, sorry, client side. Here we are using this federated average. Then sorry. Here we are using in this example I kept only this thing. So this is example only for this learning that algorithm. I didn't keep an example for this program and computation. I will give the link for this so that you can go through that like official federated learning library. So you can go through that. So I will give you at last. And next is another framework called Flavor. So this framework is actually a new framework, but here the main advantage of this framework is whatever the machine learning libraries or deep learning libraries, with the existing machine learning and deep learning frameworks, we can integrate this Flavor frameworks. So that is the main advantage of this. The previous TFF framework is mainly for research oriented academics and simulation, but this is not this is actually for integration purposes. So that is the main advantage of Flavor. So here you can integrate with the existing frameworks like PyTorch, TensorFlow, Scikit-learn, JAX. So there are n number of existing. It will easily adapt with the existing frameworks. And here it is actually like a client server architecture. So in the client side, you will have what the behavior or the mechanism or the procedure of the server is actually defined by the strategy object. So what algorithm or aggregation method you are going to use, that will be decided by this server. And in the client side, here we are going to use this package flavor.client.client, this class, and flavor.client.numpy class. So these two packages we are going to use. So using this package only, here we are having the methods, and using this class, what you can do is you can update the parameters to the server, because from the client side only we need to update the parameters, right? So it is actually done by this these two functions. So here I will show that. So this thing. So this is the class. So here you can see. Here you have to import the libraries. Okay, this one. Here you have to import that. So with the existing, it can adapt easily. So here we have imported TensorFlow as TF and FLWR as FL. So that is Flavor. Okay, so the Flavor, we won't use this FLOWER. We have to use FLWR only. So here in this class, my Flavor client, FL.client, NumPy client. And so this is the class we have created, and this is the inbuilt predefined class. And here you have segregated the data set for testing and validation, training and validation, and you have to get the parameters and fit the parameters, and finally you have to evaluate the parameters. So this is how this class, using this class, the client will get the parameters, because it has to return the parameters to the server side. Okay, so for that it will return the parameter to the server. So using this function, it will return the parameter. So next thing is file shift. So this is another framework which is actually developed by open-minded community. Here, this will enable the safe and secure transmission. It is actually mainly used for this privacy enhancement thing. The techniques like differential privacy, secure multi-party computation, and homomorphic encryption. So the thing is, instead of directly update the parameters, instead of directly send the updates to the server, what we are going to do is we are going to add some noise, or we are going to split the updates into n number of parts. Okay, so or we are going to encrypt the updates. We are not going to show the updates directly to the server. Instead, we are going to use some mechanism, or we are going to use some approach that is called differential privacy or secure multi-party computation or encryption. So we are going to use this thing, okay, instead of directly showing that. So here this is actually completely object-oriented approach. This is actually different from the previous two things. Here you are going to use 4 different terminologies. One is called worker, and in that you are going to use a virtual worker, pointers. How in the C++ we have pointers, right? So the pointers is nothing but it will hold the address of another variable. So like that it will hold the address, it will hold the reference of another data. Okay, and privacy primitives. So here we are having additive sharing tensor and plan and protocol. So the plan is nothing but the sequence operations, and the protocols is the rules to follow, like how it is going to aggregate all the updates. And this additive sharing tensor is how you are going to share the update, whether it is whether you are going to use any differential privacy, or you are going to use this SMC or this homomorphic encryption. So you have to decide here which privacy primitive you are going to use. So this is completely for this privacy ensurement. Okay, so these are the 3 different frameworks. So here this is the code for this. So you have to import these 2 libraries. So for Shift SY, and see here this one. So this hook is the torch hook torch. That is, you are going to create the worker, and this is the actually worker. This hook is the worker, and you are going to create the virtual worker. For server, you are going to create one virtual worker, and for client 1, you are going to create another virtual worker, and for client 2 also you are going to create the another virtual worker. And what is the use of this torch.tensor is, this data is the actual data. Data 1 and data 2 is the actual data. But instead of using this data 1 and data 2, you are going to use the pointer here. So this torch.tensor is the pointer here for this client 1. And this torch.tensor, that is 456, is the pointer for this client 2. So like this, we are going to use this PyShift framework, and this is all about the server side. Okay, how it is going to retrieve the model and how it is going to plan the see here, how it is going to send it to the client. The server needs to send the model to the client, right? So that is why it is everything is in command line. So we are going to consider only these 4 lines. Sorry, for this first few lines alone. So this is PyShift. So these are the different frameworks. So we have covered all the core components of the federated learning system design. So in the federated learning system design, so these are the important process. So the first step is you have to choose the framework, which framework you are going to choose. That is TensorFlow or Flavor or PyShift, which framework you are going to, so most suitable for your project, that you have to select. The network setup. So you have to ensure whether the communication protocol, what communication protocol you are going to use, gRPC, REST, and like you have to configure the TSL, that is transport layer. So you and what type of architecture you are going to use, whether it is a centralized architecture or decentralized architecture or hierarchical architecture. Then you have to configure your client. So the client should be whatever the objective function you are going to use in the client, it should be low weight, less weight, so that it will train without complexity, it will train all the informations or all the data in the client side. Then the training loop. A training loop is once the update generated by the client is sent to the server. Excuse me. So once the update is sent to the server has to aggregate all the functions, and again it needs to send the updated model to the client, right? So that is called a training loop. And a model management, so how you are going to, whether if it is a synchronized federated learning or if it is asynchronous federated learning, based on that, what type of, how you are going to handle the straggler and stall problem. So with if you want to handle the stall problem, you have to go for this versioning and evaluating. So that is initially the version 1 update which is sent by the client, and again next version which is sent by the same client. It will be stored and it will be compared, and after that it will be updated in the global model. So that is called model management. And privacy and security. So we have to make sure the privacy and security while sending the updates. So to avoid those privacy threats, we are using this secure aggregation and differential privacy methods. So the secure aggregation is nothing but masking, and the differential privacy is nothing but like you are going to add some noise with the weightage, whatever the weight you computed in the model or training during the training. And next is the challenges. This almost all the challenges we already discussed in the previous slides. So the first and foremost challenge is heterogeneity. It might be a device heterogeneity, or it might be a data heterogeneity, anything. Okay, so device data heterogeneity means we need to handle the unbalanced and independent identically distributed distributed data. See, as I said, the client which is in Chennai, the client which is in Gujarat and Delhi, Mumbai and Kashmir will have different types of data. So the data distribution of data is very if you compare the distribution of data, the difference will be too high. Okay, so we need to deal that imbalanced data also. And the client heterogeneity, different devices will be there. Some client will compute fast, some client will compute very slow, and due to some power issues, some client will be dead, and some client, due to some communication issues, some client will be facing the bandwidth issue. Like that, so different heterogeneity problem, that is device heterogeneity problem will be there. So that also we need to eradicate. And the solutions for the heterogeneity problem is, so here you can see the example. So in the first figure, this is actually the data heterogeneity problem. So this is the data which is collected from different clients. See the distribution, how it is distributed. Only this data is actually spreaded very clearly, but other data is and all like it is clumsy, and you can see the difference between the data, the variations between the data. So that is called data heterogeneity. And device heterogeneity is, let us see this client 1 and client 2. This is actually very fast, and this client is very slow, and it is not sending the messages rapidly. So the client server has to wait for a long time. That is called straggler problem. And because of this, the resource, every resource is actually wastage, right? Here it is only 2 client. If you think about just 10,000 client, because of in the 10,000 client, only because of one client, the server is the waiting for long time, means then all the resources are wastage only, right? So how we are going to deal this? This is another challenge. And in the after every model training, the client is sending the updates to the model, right? So let us consider this particular client. This particular client is sending the malicious update, or it is sending some malicious and untrustable update. So it will spoil the entire model. So then how we are going to identify that? So what you can do is you can select the client in some, by using some selectional process or some selectional approaches. So you can follow some approaches, or you can follow some techniques to select the client. Here also, let us see this client is computational speed is very high, and this client computational speed is very high, and compared to these two things, these two are very slow. So because of computational power, again the server has to wait for some time, right? So these are the challenges. So apart from these challenges, scalability. So in the place of 100 nodes, if you are going to increase some 10,000 notes suddenly, then how it is going to deal, how it is going to handle how it is going to sustain, how your model is going to sustain. So that we have to deal. And privacy concern, as I said, while sending the updates, every time while sending the updates, even while transferring the model, global model to the client, how you are going to give the privacy concern. And client dropout, as I said, due to some power failure, due to some communication issue, some client is not participated in the system, then how you are going to deal that using the asynchronous or aggregation strategies, how you are going to deal those challenges. And communication, again, because of bandwidth issue, because of high cost, and how you are going to handle this exchange of updates between the models, and exchange of update between the clients and the server. So these are the challenges you have to consider while building the system. So whatever the system, whatever the FL system you are going to build for the real-time system, based on the requirements and based on the applications, so we need to consider all these challenges and how you are going to provide the solutions for those things. So you can go for some compression techniques. So this also we discussed. So for optimizing the communication, you can use some compressed techniques. That is, you want to share the updates, then instead of sharing the raw updates, you can compress the updates. You can use the sparsification and quantization approach for sharing the updates. And partial model aggregation. So instead of the like due to some power cut or due to some communication issue, some client couldn't respond, right? So how can you deal those things is, you can include only the partial client, not all the clients. So based on that, you can avoid those things. And asynchronous training, that's what. So instead of including all the nodes, you can include only the partial nodes. And privacy issue, so using the data differential privacy and secure aggregation, we can ensure the privacy. And we can ensure the gradient leakage also, we can avoid the gradient leakage. And by introducing the proximal terms, we can handle the statistical heterogeneity. And by introducing the asynchronous federative learning, we can eradicate the synchronous heterogeneity. And by using the federative learning trust, and by detecting the anomalies in the communication channel, we can avoid the adversarial attack. And also by selecting that is fairness selection, by selecting the proper client without any bias. So for that, we are having q-fed average approach is there. So we can use that particular approach, that is q-fed approach, so that the selection will be client selection will be, that is, the client selection will be very reliable and very fairness. And deployment complexity, regarding this deployment complexity, you have to decide which framework will be very suitable, most suitable, either TFF or Flavor or 5-shift. So among this frameworks, which framework will suitable more, so that you can avoid the deployment complexity also. So these are the solutions based on the challenges or based on the applications. So you have to decide which prominent factors will solve this particular this challenge. Like that, you have to decide that. So this will actually optimize your system very well, and it will increase the performance also. Okay, now I will show the demo. Second. So this one, My screen is visible? You're able to see the.
Yes, visible now, visible.
Yes, okay. Okay, so this is actually openly available source code only. From first, I will show the framework. So here, actually, this framework is from Flower. Here, what framework we used is Flower framework. I will show the web page. So this is flower.ai. So in this web page, you can use this Flower framework and you can design your projects. So a lot of libraries are available. So here you can use this, and a lot of demo also there. So you can request for some demo and you can use that. And this regarding this demo, this actually I got it from the web page, and I will share that link also. I didn't do this, but we can try with this using this this Flower framework. So we can try, but still I tried to simulate some federated learning framework. This is actually, I didn't deploy any model here, but I tried to simulate the federated learning. I didn't use any Flower framework or TensorFlow framework. Just I tried to simulate how the federated learning is going to system will work behind the thing. So that initially we will be having the global model, and the global model will be trained in the client. Different clients will be there, and I created some n number of clients. So I will show that. See here. So here I used this MNIST data set, that is digital digits data set. This is that's what I said. I didn't use any federated learning framework here. I just used the traditional TensorFlow, NumPy, Matplotlib framework. So these libraries only I used. Again, I'm saying I didn't use any federated learning framework here. This is actually simulation. So this things I want to show is here I tried to segregate 5 different clients. Right, I will show from the starting one. So this is the library, and I loaded the data set here. I just reshaped and normalized pre-processing, all the pre-processing. I just displayed the few samples here, and this is the overall data distribution. This thing is the overall distribution. You can see the distribution here, not too much deviated, right? So very slightly deviated, but not too much deviated here. So you can see the distribution here. And I built a CNN model, a simple CNN model only, a basic CNN model. So you can see only one convolution layer with a ReLU activation function and max pooling layer, one flattened layer, and finally activation functions, classification layer and activation function. So and the optimizer I used is Adam optimizer. And last function is sparse categorical last function I used. And the quantitative metrics I used is accuracy. A simple CNN model I used. And this is for training and testing. And okay. So this actually should comes later, but still okay. So here what I did is I tried to I tried to create a virtual client, 5 different clients. So this is the thing, 5 different clients. So now the data is segregated, splitted into 5 different clients. And if you see the data, so this is the data. I splitted the data for 5 different clients. So see the data which is stored in the client 1, and this is the data distribution. And this is the data which is stored in the client 2, and this is the data distribution. And this is like this. I distribute randomly. I didn't use any strategy for splitting the data set. Just whatever the data set which is present in MNIST, I just segregated into 5 different categories, 5 different clients. So I created my virtual 5 different clients. Okay, now the next thing is one second. Here, and this is also another distribution graph only. So here I tried to include some unbalanced data in that thing. So again, this is the data distributed graph, and this is also the confusion matrix for this here. Now the federated learning starts here. Also, I have shown this one also. Now see this. This is the epochs of traditional deep learning. So whatever the deep learning I used. So the same code only, I just compiled in a single tab. See here. So I am loading the data set. Is it visible or do I need to zoom? See, so here, this is the data distribution. So here I have defined the traditional CNN model, and this is the centralized 10 epochs. And here I created the client, 5 different clients. And this is the code for federated learning. So here what I did is, I initialized the global model, and round I created as 5 rounds. The client needs to update the weight for 5 times. Are you getting? The client needs to update the weight for 5 times. So every one time it will update, the global model will get update. Again, the model will be transferred to the client. Again, the client will train the model, and again it will transfer the update. Again, the model gets update, the model will be transferred to the client. Like this, it needs to do 5 times. That is called 5 rounds. Okay, so here it is initialized, and the model is trained locally in 5 different clients here, and it will collect all the weight. Here the aggregated algorithm or aggregated technique what I used is fed average. So here it is just going to take the average alone. So finally, I tried to compare the result, which is by the centralized accuracy and federal accuracy. So I will show the output now. So this is the sample image, and this is the overall data distribution. And this result is achieved by the convolution neural network. Overall accuracy is 98%. And 10 epochs I use. I gave 10 epochs. If I would have give 2 more epochs, might be it will give some 100%. I'm not sure. So this is traditional CNN model. And next thing is, this is the federated learning client 1. This is client 2, client 3, client 4, client 5. Okay, this is a non-IID data I tried to add, but it didn't work properly. So now, and a round I gave is 5 rounds. So this is the output which is given by the federated learning. So if you see the accuracy here, see in the centralized accuracy it is 98 actually, but in the federal accuracy it is 77.67. But still we are trying to simulate, right? We are not doing the exact thing, and we don't have the proper data set also. So it is somewhat the fluctuation is there between the centralized. The centralized is nothing but the CNN, traditional CNN. And this federated learning accuracy is 97.6. So this is how it is done. This is a simulation, basic simulation I done. But now, this is actually a federated learning using Flower framework. So here, these are the libraries packages you have to install using this pip install Flower simulation, Torch Vision, Matplotlib. So that you have to install. And the next thing is, so these are the libraries you have to import. So the main thing is Flower, and Torch Vision, and Flower.com and metrics. So here, what are all the metrics you are going to use? For that, you have to include this library. And the data set used is Cipher 10. So Cipher 10 is like a 10 different objects will be there in the data set, and it is used for classification. And this is just here I tried to print the versions, different versions of the Flower, NumPy, Torch libraries, all the thing. And it is I kept here as CPU, not GPU. So it is CPU. And now it is data. So what are all the data available in the data set? It is some random images, plane, car, birds, cat, deer, like that. And the client I am going to fix is 10 clients. So here also we are trying to create a virtual client, but we are using the federated learning algorithm. But in the previous case, we didn't use the federated learning library. We didn't use any federated learning framework. We just tried to simulate the thing, but only we used the aggregated function. We just tried to aggregate all the functions. That is what that is the difference between simulation and system design. So here we tried to deploy the model. We tried to use the federated learning uh, algorithm. So here, this is batch size. So this is all about the data set. We are trying to load the data set here, and we are we are just splitting the data set for training and testing. And here, this is actually for 10 partitions. Why? Because we are trying to create 10 clients. So for that, we are trying to split the data into 10 partitions. And after that, in each partition, we need to split the data for training and testing, right? So this is inside the client, we are splitting the data for training and testing, and we are loading the data here. Okay. And next thing is, this is actually just some random image just for just I printed this. So you can see this is truck, this is car, this is plane, this is car, frog, like this. So it will showcase all the things. Now, this is the classical centralized training. So classical centralized training is nothing but some classical CNN model. So this is also a CNN model. See, the thing is, it is not restrictive to deep learning model. We can go for machine learning model also. We can use some machine learning model. We can go for optimization techniques. We can use any model, either machine learning model or deep learning model. We can go for anything. But here I used, since it is under the data set also, it is not only for image. We can go for any other data set also. CSV file, any file we can go. But here I used image. So this is the CNN model, traditional conventional CNN model. And so this is the accuracy of each epoch, accuracy from the for the traditional CNN model. Okay, so you can see the accuracy here. It is accuracy is 47% and loss is 0.04%. Okay, like if you have increase your epoch, your accuracy might also get improved, I guess. This is a simple CNN model, right? We are not using any pre-trained model, just a random CNN model. So the accuracy is very poor. So no issues. We are not going to worry about that now. We are going to concentrate about the federated learning with Flower. See here, this is the our algorithm, our framework here. So see this, we need, so as I said, we have to use this function, get parameter and set parameter. So this get parameter, it will return the updates, local parameter to the client, sorry, server. And the set parameter, it is actually set by the server side. Okay. So these two things. And this is, see here, this we have seen in the Flower thing, right? This is the class Flower client, fl.client.numpy client. So this is the class. In this class, we need to use this get parameter, fit parameter, and evaluate parameter. So using these three functions only, we can return the parameter to the server, and we can fit the parameter to the model, and we can evaluate the model whatever the model which is in the client side. So this particular block is completely for client. This particular block, it is completely for client, and this is for server side. Okay. Then okay, we'll see this is weighted average here, where we have used this here it is. See this, we have used this fed average method, and this is the final output. And see the accuracy here, the accuracy is this one. In round 1, it is 0.06, round 2. So here the round also we kept as 10 rounds. So in the each round, it is the accuracy is 0.05, 0.04, something like this. So it is very somewhat related to centralized accuracy also. Even the centralized accuracy also, it is somewhat 0.55 only. It is 0.44, I guess. So this is the demo. And so this is actually openly available code. You can use this code. It is available, and I have given the link also in the PPT. I will share that link, and you can go through this comics page, which is actually it is very interesting. So later you can go through this comic page. And what else I want to share? I guess not. That's it. And I have shared the links which is given in the PPT, so you can go through the links, whatever I shared in this. So I guess I'm done. Any queries?
Dear
So,
participants, yes, ma'am.
yes, ma'am.
Yeah. Dear participants, do you have any queries? Please unmute yourself and raise your queries. Ma'am is with us to clarify your queries, please. Anyone having any doubt? Dear participants, hello. Yes, no queries.
No queries?
No queries from participant side, ma'am.
Okay, fine. Okay, thank you. Thank you for the opportunity, ma'am.
Yes, ma'am. Yes, ma'am. Thank you, ma'am. On behalf of our institution and all the participants of this faculty development program, I would like to express our heartfelt gratitude to you, ma'am, for delivering such an informative and insightful session, ma'am, on this federated learning and system design. Ma'am, your clear explanation of this concept and your ability to present this advanced topic in a structured and engaging manner made this session highly valuable for all of us. Your expertise in artificial intelligence, machine learning, and related emerging technologies was clearly reflected throughout your presentation, ma'am. The knowledge, practical perspective, and valuable insights you shared have greatly enhanced our understanding of federated learning and its significance in modern intelligence systems, ma'am. We sincerely appreciate your valuable time, effort, and willingness to share your expertise with us. Your dedication to academic excellence and knowledge sharing is truly inspiring, ma'am. It has been a privilege to have you with as our resource person for this session. We are grateful for your contribution in making this faculty development program more enriching and meaningful for all the participants. Once again, thank you so much, ma'am, for your excellent session and valuable guidance. Thank you so much, ma'am.
Thank you, ma'am.
Thank you, sir. Thank you, everyone. Shall I wind up? Anything else to?
Yes, ma'am. No problem. Yes, ma'am.
Thank you, everyone.
ma'am.
Thank you,
Thank you, ma'am.
participants. Thank you,
Yes.
Dr. Purnima, ma'am. Thank you, all the coordinators, organizers for this FDP.
Thank you so much, ma'am.
Everyone.
Very excellent session, ma'am. Yes, ma'am.
Thank you very much, ma'am. Thank you for the patience. Thank you for everything. Thank you, ma'am. Meet you soon in the another program.
Sure, ma'am. Thank you so much. Dear participants, please submit the feedback form. And once you have submitted means you kindly leave the meeting. Already we have posted that feedback form link in chat box. Kindly request everyone to submit the form.
One request from my side, Purnima,
Yes, ma'am.
have you
Purnima,
taken
ma'am.
screenshots?
Yes, ma'am.
Have you taken any screenshots, ma'am?
Yes, ma'am. I will send you, ma'am.
Okay, ma'am. Thank you for that. Thank you, ma'am.
Thank you, ma'am.
So dear participants, with this today's program concludes. Thank you for your valuable participation and support. I kindly request everyone to rejoin tomorrow using the same meeting link by 8:50 a.m. as the session will commence promptly at 9 a.m. Thank you so much, participants.
Got it.